Okay, I guess we can start. What do you think, Lorenzo and Massimo?
Sí, yes, for me, oui, perfect.
Okay. So, welcome everybody. Good morning or good afternoon, depending on where you are. And I'm happy to have you here in this second slot of this parallel session on standard cosmological probes. Yesterday, we had an interesting first session discussing about quasar, GRB, intensity mapping, surface brightness fluctuation, cosmic chronometers. Today, we will have other extremely interesting talk touching gravitational waves, redshift rates, so on and so forth. And without further waiting, I will leave the floor to the first speakers of today, which is Daniel Holtz, which will present us about cosmology with gravitational gravitational waves. And just a communication to the speaker, I will give you a warning at the 70 minutes so that you can understand where you are. Please.
Thank you very much. Hold on, my screen share has disappeared, so let me screen share again. Hopefully this works. And there we are. Okay. All right. Thank you to the organizers for inviting me and for organizing this very interesting couple of sessions. I think it's really worthwhile to think about, other ways to probe cosmology, especially in an era when there are disagreements and people are starting to go to desperate measures to explain what's being seen. It makes sense to really try to buttress the data that we have, and I think that's what all of us in these sessions are interested in doing. So I'll focus on standard sirens as one of the ways that you kind of get independent measurements of cosmology. And so, my goal, since it's very short, we only have 20 minutes, I will give a brief overview and then just focus on some recent results, focusing mostly on my own work. I'm not trying to make a broad overview of the subject. It is interesting because, of course, this subject didn't really exist 5 years ago or 6 years ago, and now there are tons of papers and it's actually hard to keep track. So it's remarkable how things change. Okay. So I'll just give the basic overview just to make sure that we're all on the same page. So the basic idea of gravitational wave standard sirens is that black holes are actually quite simple, unlike many objects in astrophysics or cosmology. Black holes really are only described by a couple of numbers. You have mass and you have spin. Charge is irrelevant. Spin, okay, you have directions and relative to the orbital angular momentum. But basically, these are really simple objects, and they're fully understood from first principles. So when you take that into account, and Bernie Schutz was the first to realize this, what you end up with is a unique way to measure luminosity distance. And it's a direct, absolute measurement of luminosity distance. And the way I like to think about it is that your luminosity distance is just being calibrated by the theory of general relativity. So you have a source, you measure its gravitational wave waveform, as I'm thinking, binary coalescence, and then the calibration is provided by GR. Now, to actually use this for cosmology, distance isn't enough. In general, you also need redshift or something else to tie. And in general, in this approach that I'll talk about, especially towards the end, I'll talk about other ways. In general, you need an independent way to measure redshift. And so a lot of what I'll talk about has to do with how do you find that independent way to find the redshift. Okay. I think I'll just skip this entirely. This just was to show exactly how you extract distance from the gravitational wave waveform, but if there are any questions, I can go back to that. I'll skip this as well. This was just to show that if you have the redshift and you have the distance, you measure cosmology, but everyone here already knows that. Okay, so in general, for standard sirens, there are two approaches. One is the counterpart or bright siren approach, and one is the statistical or dark siren approach. And I'm going to go through each of these in turn. So let me start with the bright siren approach, and this is kind of the canonical one. This is the one I think most people are familiar with. And in this one, the gravitational waves give you a distance to a source, and if you also get photons, you can identify the host galaxy or maybe the source itself and get a redshift. And by combining that, you get distance and redshift for the same source, and you're off and running. So this is a very clean and direct way to measure luminosity distance and put points on the distance redshift curve. The problem is you need an EM counterpart. And so it's of limited utility because you need a very special type of source. Of course, we all know this, but 1708-17 was the ideal standard siren. And it's quite remarkable that the very first one that we detect multi-band gravitational waves and electromagnetic turns out to be so perfect. It had an optical counterpart. We got the redshift of the host galaxy. If anything, I mean, so this is it. Like this was what we were thinking about when we talk about standard sirens. If anything, it's probably too good. It was so loud, in part because it was really close, and it was so close, in fact, that there were lots of additional issues, sources of noise on the measurement, including peculiar motions and bulk flow and various other things that had to be corrected. So this really was an extraordinary and very unusual event. And I mean, I'm talking about standard sirens. I have to at least show this plot, which was the posteriors on our estimate of the Hubble constant from this one source. So this is just the first source ever. There's only one, calibrated by GR, and this shows our estimate of H0. And it's in more or less the right region, which at least to me was a great relief. I mean, it could have been anywhere. It's really the first time we're doing this. The fact that it works, I think, is quite shocking and reassuring. Of course, the error bars are quite large. I mean, this is the very first one. And remember, this is a really good one. If anything, too good. Part of the errors here have to do with, additional uncertainties because of peculiar motions and bulk velocities. The main source of the error, and this will be kind of a theme when you talk about standard sirens, has to do with the distance inclination degeneracy. So for a binary system, if it's face on, it's a little louder, and if it's edge on, it's a little less loud. And you can think of that just in terms of polarization, if you like. But in any case, what that means is that a loud source far away and a loud source face on, so a face on source far away and an edge on source or a softer source closer by look the same, have the same luminosity, or have the equivalent loudness in our detectors. And so it's difficult for us to break that degeneracy currently with the network we have, and that just adds errors. But if you know the inclination, you can improve cosmology, and if you assume cosmology, of course, you can infer the inclination. And this is one example where, for this source, there's a claim of being able to measure the inclination directly through properties of the afterglow based on radio observations. And if you take those at face value, then you improve your measurement of the gravitational waves. Now, of course, this incorporates systematics. One of the great things about standard sirens is if you're just calibrating by GR, at that level, there are no systematics, or the systematics are very different. But when you start bringing in astrophysics, now you're introducing new systematics, and it makes things much messier. But it has the potential to improve as well. Okay, So now I'll switch gears and talk about the dark sirens, or the statistical method. And this was the method that Bernie Schutz actually initially proposed in his paper in 1986. And the idea here is you don't have a counterpart, for example, binary black holes. We don't expect any optical counterparts. If you don't have a counterpart, then what you can do is use all the host galaxies in the volume, all the galaxies that are there. Each one is a potential host. You can do the analysis for each of those. And if you do that for many different sources, the galaxies that are the true hosts will lead to kind of the peaks stacking up on each other, and then you'll end up converging on the right value of H naught. So that's the idea. The first time this was done was actually for 1708-17. This was an analysis led by Maya Fischbach. And what she did was she took 1708-17 and ignored the fact that we knew which galaxy was the host, and just did the statistical analysis of all the galaxies in the volume. And what was nice about this is it's a small enough volume that we can actually do a decent measurement statistically, and then we can kind of get some sense of how well this method works. And here's what we found. So the kind of pink line here is what you get assuming the counterpart. So this is the bright siren approach. And the dark siren approach gives you these other lines where you kind of have to weight things and have cutoffs on what counts as a galaxy. And as you vary that, you get different distributions. They're not as good, but they more or less agree, which is another way to say there's actually a small cluster of which NGC 4993 is a member, which dominates the mass in this volume. And therefore, even if you pick galaxies sort of at random, you're going to get more or less the right value most of the time. And that actually turns out to be a theme for a lot of the dark siren work. So this is actually dark siren work. I think this is the first dark siren approach on an actual dark siren, which was 1908-14. And you see there these curves. So what you're supposed to do now is kind of look at these kind of blue curves compared to the red curve, and you see they're very broad and they have a lot of structure to them. That's just because there are lots of galaxies in the volume. And here's yet another one. This is kind of the LIGO collaboration paper on this. And again, this is all the black holes based on O2 up to O2 data. And here is what you get if you have a counterpart. And again, you can see, you don't get that much data from the black holes. The statistical method is actually kind of weak. The volumes are large. There are just too many galaxies in those volumes. One bright siren completely overwhelms many, many dark sirens. And here's yet another one. This is a recent paper, and this paper is extraordinarily thorough, and there's a public code associated with it. I'm really excited about this group, and they're completely independent from all the LIGO efforts I've been showing previously. And they also, find a similar thing where you kind of remember, you can look at the axis here. It's a very broad axis, and you get some peaks where there's structure in your volume, but it's still extremely broad. Okay. And this is just a paper kind of summarizing what we see as the future of standard siren cosmology. This is from a couple of years ago and needs to be updated at this point, but it captures the basic message, which is these curves above are the dark siren approaches. And you can see this is how well you measure H0, and they converge pretty slowly. And you don't get below 10% for a while for the counterpart cases, the bright sirens, it converges much quicker. This all depends on the numbers. I mean, if 1708-17 is the last bright siren we get for the next 20 years, then we're going to stay here at 10% or 15%. But assuming we get more, and so this is all projections, a few more of those will start to converge quite quickly. And this is another way to show that. I'll skip that. I should mention, as everyone knows, precision cosmology, even if you get just an improvement on H0, that actually has, even just H0 has an impact on cosmology more broadly. And what we're talking about now going forward is not just H0, but of course, all of h of z. And so out to higher redshift, and I'll talk more about that shortly. Okay, I should mention there are systematics, and it's important to keep this in mind. You know, some of them, like peculiar velocities, will go away as our sources get farther and farther away. But some of the properties of the galaxies and the selection, especially in the dark sign work, are, you know, more worrisome. Probably the biggest systematic right now, and I think this is a sign of the power of this method, is the absolute calibration of the detectors themselves. What is the response of the detector? It's not kind of astrophysical uncertainty. It really is, do we understand our instrument well enough? And the calibration group within LIGO just put out a very nice a document on the archive going through their calibration, how it works, and where things are headed. So if you're interested in that, I highly recommend that. Oh, I'll just mention as an aside, just because I'm excited about this, 170817 is such a great source that it actually gives us the ability to calibrate the LIGO detectors, or the LIGO Virgo detectors directly. Since if you assume GR is right, you know the shape of the waveform, you can then look in your detector and make sure that the waveform you see is consistent with GR as a, say, for example, as a function of frequency. And if the response were different at different frequencies, like, you know, we get more sensitive at some frequencies than others, and we haven't calibrated that properly, we would see it. And so you can directly use something like 170817 to calibrate the detector. And given that, you know, 6 years ago, we weren't sure we would ever detect anything, the idea that we now have a source that we can actually use to, in some sense, calibrate, I mean, I think that's amazing. It's not a great calibration, but still, it's, you know, at the tenths of percent level, we can tell that the machine is working properly. Okay, so I figure I'll spend my remaining time on non-standard standard siren approaches, just to give you some sense of some of the other things that are going on now, and just to give you some sense of the power of this. And it's just because it's a brand new field, we're still figuring things out, and as we go along, we have new ideas of how to do this. And so this is one example which I'm particularly excited about, which has to do with the fact that LIGO Virgo are missing the big black holes. If you look at the population of black holes that have been detected, you see that at around 40 or 50, that population starts to drop. And this was first noticed in a paper led by Maya in 2017, where we asked, where are the big black holes? And the answer was, they're missing. And that's now been confirmed many times over. And this is the latest paper. This is now published. This is the populations paper from 03A, the first half of the third observing run. So it's the latest population estimate. And what you see is this is just a distribution of mass of the primary in black hole binaries. And you see that the masses are, you know, sort of flat and then taper off, drop. And this is a log plot. So this is a pretty dramatic drop here. And I should say this is an observer frame. And so in the source frame, the observer frame, we're actually more sensitive to big black holes. And so you have to, you know, take that into account when you move to the source frame. Okay, there is a drop. All the models show there's a drop. It may be perfect, or there may be a few interlopers in that drop, but what we know for sure is that there are fewer bigger black holes. This is as expected from the parent stability supernova gap. I won't get into that now, but the bottom line is, you know, there's some theory that says there should be a drop. When we look at the data, we see a drop. Now that drop is a drop in mass. Mass redshifts. As you go to higher and higher redshift, the waveform redshifts and the detector frame mass shifts to higher and higher masses. Because you go to lower and lower frequency. And so that is a feature that you can use to infer redshift. And so in this work led by Will Farr, we showed that you can use this feature to then infer cosmology. And so this means you use the binary black hole distribution, the mass distribution, to measure cosmology. And it turns out it works extraordinarily well to quite high redshift. You get measurements of 2% at redshift of 0.75. So, and
Just
here's kind of
comment
estimates. Yes.
That you are 18 minutes.
Okay. All right. So great. Thank you. So this is extremely powerful and exciting for the future. This is, this is with advanced LIGO. So in the next few years, advanced LIGO Virgo will be starting to measure just with the mass distribution of the binary black holes at the level of % over a wide range of redshifts. There are, of course, systematics you can worry about here. You're now using a feature in the mass distribution, but we have reasons to think those might be under control. And again, this is all just completely independent. I should also mention, so this is in a recent paper led by Jose Maria Escriaga, postdoc at UChicago, where we looked at the same thing that I just discussed, this mass gap, but now we looked at the upper end of the mass gap. And we argue there should be far side black holes on the far side of the parent stability supernova gap. That's what theory says should happen. And those could also be used to measure cosmology. Sorry about this. And you get interesting measurements. It depends on the numbers. And these are sources for both LIGO and LISA. Exactly what happens here is very uncertain because we've never detected these systems, but they're potentially very exciting as well. And I'm going to just spend my last slide on this paper that just went up a couple of weeks ago, which is yet another way to do standard siren work, where instead of using a redshift, what we do is we use the equation of state of the neutron star to break the degeneracy and infer redshift. And the idea here is, if you know the equation of state of neutron stars, or it's something you can measure, then for example, if you knew all neutron stars were 1.4 solar masses, you could use that. You would measure a redshifted mass for your binary. If you know the source mass, you can figure out the redshift directly. And therefore, you can do this standard sirens. You can do the exact same thing here. We don't know the neutron stars have a diversity of masses, but there should be only one equation of state describing the neutron stars. This can be, this is described by the love relations. So there are these very nice relations that relate the tidal deformabilities of neutron stars. You can use the love relation, take a few neutron stars, kind of calibrate things, and then the rest of the neutron star population automatically gives you the redshifts. And we show that, this is a difficult game. You need a lot of neutron stars, but you get to the % level with Cosmic Explorer, even without any counterparts. So this is a pure kind of gravitational wave measurement that gives you luminosity distance redshift points. So it's just a completely different way to do things. And that's what's kind of exciting about this. In this field, you keep coming up with kind of new ways. All of these are completely independent from the standard ways, which of course is the theme of this whole session. Okay, I'll just flash up the group at UChicago, and I'll just end by saying, this is just kind of the beginning. We're getting more and more sources. We turn back on hopefully in just over a year, and then we'll see what happens next. But standard siren cosmology has definitely arrived, and I think it's here to stay. Okay, I'll end there.
Thank you very much. So maybe we have time for a quick question. If not, I actually have a very quick question. If you can give some quick comment about the dark science, if you can tell very little, some details about which catalog one would need to do such calibration, which depth.
Yeah, so that's probably the hardest part of this is figuring out the galaxy catalog. So for the results I showed, there were 2 catalogs being used. One was the GLADE catalog, which is a catalog that a group within Virgo has been building, which is, has reasonable completeness. And it's really a compilation of many different catalogs. The other one that we used, and that was the second one, the second paper, which was led by Antonella Palmisi, and Antonella in that one used the DES catalog, the gold catalog, Y3 gold catalog, which of course is just in the DES footprint, but for the sources that were relevant there, they were in the footprint, and that catalog is uniform and is better understood, but it's only for that part of the sky. In both of these cases, there are a lot of subtle issues that come up. The one that I had the hardest time with was just the issue of photo Z's, how you estimate the redshifts and whether there are biases in that, and it's a very tricky thing. That is in general set up for weak lensing and works well for weak lensing. It's not set up for dark sirens. And I think there are lots of complications and subtleties there that took us a while to work through. But yes, I mean, going forward, if you really want to do this, having good catalogs is essential.
Okay, thank you. I saw that there are other questions. Maybe we can leave those for the discussion at the end, and we can continue with the program. If you want to write them maybe in the chat, we can collect them for the end of the discussion session. So I would move to the second speaker of today, which is Alice Pisani, which will talk us about unveiling the universe with cosmic voids.
That is correct. Thanks, Michele. Okay, I'll share my screen. Please let me know if you can hear me and can see my slides. I will go to full screen.
Yeah.
Let's see. Okay. Okay, hopefully this will work. Feel free to interrupt me if at any time something is unclear. So first of all, I would like to thank the organizers of the session for inviting me to talk about my work with voids today. So unraveling the universe with cosmic voids, I would like to highlight that this is, of course, work done in collaboration with many people all around the world, in particular Nico Maus in Munich, but also great students, both graduate students and undergrads. I have the pleasure to work with both in the US and in Italy, typically. So let's talk about cosmic voids. We know that nowadays, and I'll be very brief on this, we are in the era of precision cosmology, but even though we have a standard model, lambda CDM, we still don't know what dark matter is, and we don't know what dark energy is. So this 95% of the universe that we don't understand is pointing to new physics. Basically, the idea is that we can use standard probes, but there is a lot to learn if we think creatively about other ways of using tools that we have in cosmology nowadays. And so one of the tools that we have is the large scale structure of the universe, as you all know. You can see here two maps of the distribution of galaxies, and you can see that we have, I hope you can see my cursor, that you have overdense regions. Every point here corresponds to a galaxy, of course, and we have regions that are called clusters of galaxies. And then we have filaments, these elongated, slightly overdense regions. And finally, the regions on which I am interested most are parts of the cosmic web where we have very few galaxies, and those are called cosmic voids. And you see that nowadays we have extremely dense and beautiful data set. This is only 3%, for example, of the latest Slow and Digital Sky Survey data release. I think this is the BUS sample, and you can really see that the underdense regions are mapped in detail. So cosmic voids are the only regions for which we both need to have extremely large volume, but also deep and detailed maps to detect the faintest galaxies, and so be able to map the density profiles and features of those voids. But we can ask ourselves, why are voids interesting for cosmology? And so in order to do this, we need to think that by definition, cosmic voids are regions where we have very little matter. And if we have very little matter, they are kind of the only regions in the universe that are dark energy dominated. They're also the first regions that have been dominated by this component. So it makes sense to look into cosmic voids to understand dark energy. Also, the large size of cosmic voids and their low density mimics the current accelerated expansion status of the universe. So it makes sense to look at voids to better understand what is going on. We also know that voids are a sweet spot for potential deviation from general relativity. Those will be more prominent because of the way those deviations are defined through screening mechanisms. And finally, from the cosmology side, we know that generically, voids are sensitive to diffuse components. And an obvious and interesting example is, of course, neutrino masses. So if we want to think about some other reasons for which voids are great tools for cosmology, we also have to understand that most of the analysis of the large maps that we have use basically the two-point correlation function, as most of you, of course, know. Just take one random galaxy and ask how likely it is to find another galaxy at a certain distance from it. But there is a huge amount of information in this map that we're not looking at. And so voids can access that information. Voids have multi-scale sensitivity because they have sizes that span from tens to hundreds of megaparsecs. And we believe that they're easy to model because on the one side, we can exploit traditional techniques. And on the others, we know that models with voids keep their validity down to the smallest scales. Finally, because there is very little going on inside voids, very little gastrophysics, we know that they kind of keep memory of the initial conditions. And finally, last but not the least, we have a huge amount of data that is coming on in upcoming years. So citing here SphereX, Euclid, Roman, the Rubin Observatory, we will have so many galaxies to find or voids that we can really say it is the golden age of voids that is opening in the next decade or so. But now, how do we detect voids in observations? I will not go through the details, but I will mention that we have a void finder that is called VID. That is the French word for void. And VID has been used on a large set of different both data sets and simulations. So a bunch of data releases from the Sloan Digital Sky Survey on photometric data. And it is also in use within the preparation of the next generation of surveys. So Euclid, Roman, PFS, and DESI. So one of the big advantages, you see here a slice of a simulation. Every point is a galaxy, of course, and these are the voids that the void finder will find. So one of the biggest advantages of VID is that it provides detailed information about the shape of voids. So it doesn't have any a priori on that shape. And so it will provide us with void centers, void radii, and tracers. So combining this information, we can build a set of statistics that I will mention today: the void galaxy cross correlation function, the number of voids, and the void-void correlation function. So let's start with the first one. When we think about voids, they are very irregular on a one-to-one basis. So what we do in order to extract information is that we take many of them and we stack them. Now, because we are in a homogeneous and isotropic universe, there is no reason for which there is a preferential direction. So void stacks will be spherically symmetric in real space. And so basically one can describe the density profile of a void as a function of radius, where you see it has the underdense region in the center and then this wall enclosing the void. So this is really the void galaxy cross correlation function, because it gives the probability of having galaxies at a certain distance from a void center. And that probability increases when I get farther from the void center. However, even if voids are spherically symmetric in real space, we observe voids in Ricci space. And so what happens is that we're going to observe the extent of the void along the line of sight and its angular size. And we have to convert those into distances. And of course, you all probably know this, but we do this considering that we need to introduce the angular diameter distance and the Hubble h of z, the Hubble parameter here. And so what we have is that if we measure the shape of voids that is distorted along the line of sight, we can basically have a measure of this product. Now, it turns out that we can basically predict what is the value for this product and in a given cosmology. So we're going to, for example, pick a value of omega m or a value of omega lambda, and we're going to calculate the expected value for this product. And so if we do the ratio of the measured with respect to the expected, well, we're going to get this Alka-Pszczycki parameter called epsilon. So if we picked the right cosmology, this ratio will be equal to 1. Otherwise, it's different from 1. So we can use voids as standard spheres to test whether we have the good composition for our universe. This seems simple. We have an observed shape and we measure it. But unfortunately, or maybe fortunately, there is another effect that plays a role here, and that is the effect of peculiar velocities. So basically, you see that we have the galaxies that belong to the void here will have peculiar velocities that will change and distort the observed shape of void's profile. So the very first paper will try to mitigate this information in order to extract the Al-Kapacitsky information. But as a matter of fact, velocities of galaxies around void embed cosmological information, because by assuming mass conservation at linear order, we can see that they are defined through the growth rate of structure, which basically tells us how structures grow with respect to the expansion of the universe. So if we can measure and model the observed shape of voids, so modeling both the Al-Kapacitsky effect, the real profile, and the impact of velocities, we can gain a lot of information about our universe. And this is really what I have been focusing my work on in the past years. So we now have a state-of-the-art theoretical model where basically we're able to predict the pattern of velocities thanks to a linear model. We account for Al-Kapacitsky distortions. And finally, we added a very last ingredient here, that is the fact that we do not rely on simulations to predict the real space density profile of the void, because basically what we do is we take the real space density profile and we distort it considering the cosmology and the peculiar velocities, and then we check how that matches with observations. And so in order to get the initial real space density profile, we were taking this from simulations in the past. But right now we have a better calibration-free method. So we obtain it from data. We project the void along the line of sight, so removing the distortions, and then we make a reconstruction using the Abel inverse transform, as is shown in this plot. So we have a setup that allows us to predict what will be the shape of observed voids in a given cosmology. So let's look at this a bit more in detail. With the latest data set of the BOSS survey, we are able to test whether our model works or not. So we first took a bunch of mocks. And this is basically the 2D density profile of a void. And you can see it's underdense in the center. So the color here is giving you the density. And then you have an overdense shell enclosing the void. And you see the density contours that are measured in the mocks in black, and the theoretical model that we built in white, and you see that they overlap really well. So we have a very good understanding of what is going on, which means that we can then apply this model to data. Of course, it is more noisy because we don't have many mocks, but just one realization. But you see that we describe pretty well what is observed when stacking many, many voids and observing the density profile in 2D. And so now, because there are cosmological parameters in this prediction, we can use the match between data and the theoretical model to extract cosmological information. And how do we do this? Well, of course, we look at the likelihood that we can have here, and we extract the constraints on the cosmological parameters of interest. So to be more precise, we constrain the Al-Kapacitsky parameter that I mentioned before, and then we constrain the growth rate of structure divided by bias, because we're not looking at voids in the dark matter, we're looking at voids in the galaxy distribution. So we also have bias to take into account. And so these quantities will depend, for example, on the matter content of the universe. So we can get a fully independent constraint on the matter content of the universe, which is of course very interesting because it can then be combined. Now, the level of precision for this constraint is pretty striking, considering that it's obtained from voids only, so no CMB, for example, here, and no other combination of probes. We can also ask ourselves another question, and that is, what if we still want to use simulations to improve the modeling of the profile? So if we do this, we have even better constraints. But of course, this is at the price of losing the independence of our model from simulations that, of course, have a given cosmology. So this really shows you that this methodology works pretty well. And this has been made clear in past years. So 10 years ago, this plot was not existing. When I made it, I put in all the constraints that we have nowadays using the void density profile. And you can see that we have on top the constraints from the redshift space distortion, so the part due to velocities, and on the bottom, the constraints obtained thanks to the Al-Kapacitsky parameter constraint that we can get also from the shape of voids. And so the theoretical prediction is given by this gray line. And you see that we have a bunch of measurements from different surveys and from different methodologies. So it is a field of research that is really exploding in the last years. And now now the latest data that I have discussed today are this one. So here we have the model independent measurements. And then if we plug in some knowledge from the simulations, you get the version that is calibrated on MOX. So we really see that we have a way to get a fully independent methodology and also then shrink error bars if we additionally add in some information from simulations. Okay, so this is for the shape of voids, so the void galaxy cross correlation function. But there is something else that we can do when we look at galaxy maps and we find voids in those maps. We can also just count voids. So how do we estimate void numbers? All the results that I have shown you in the past slides are obtained with roughly 6,000 voids. And I told you at the beginning of this talk that we are in the golden age of voids. How can we predict how many voids we're going to have? Well, we have a simple excursion set model that is able to predict void numbers. It considers that voids will evolve, emptying themselves. And we have a characteristic under density that we can consider to predict voids of that particular depth. And then we can consider how thick is the redshift slice that we're considering and what is the size of the voids that we want to consider, and then what is the volume of the survey. And this prediction allows us to know how many voids we're going to have. Now, one interesting point is that it turns out that the void size function, so number of voids as a function of size, also called void abundance, so void numbers, is sensitive to the properties of dark energy. And this makes sense because we can think that the moment when dark energy becomes relevant and how strong it is will impact how voids evolve, because those are objects that are dominated by dark energy. And this is what you see in this plot here. By changing the dark energy equation of state, we can have different void numbers in the theoretical model. So this also allows us to predict how many voids we're going to have in the future. It turns out we expect of the order of 10 to the 5 voids per survey. So we're going to have a huge increase in statistics that will be very helpful for the methods that I discussed before that are already very powerful with only 6,000 voids. Now, what do we need to do to fully use void number counts to extract cosmological information? Well, there is, as for any recent probe, a lot to do. As a matter of fact, one of the biggest caveats that we have is the fact that we have a theoretical model that predicts the number of voids, but those are idealized voids in the dark matter distribution, and real objects are way more complex. So to simplify a little bit, and this is work I've been doing with two very good students within the Euclid collaboration typically, we have to account for the tracer bias, so account for the fact that we find, again, voids in the tracer distribution and not in the dark matter distribution. And we also have to account for the fact that we need to rescale voids to account for the actual underdensity in the center of the void, because the void finder will include the overdense shell of the void in its definition. So it's just a matter of understanding what is the difference between what is predicted by theory and what you observe, and just make a rescaling of the size. Luckily, this works pretty well. And this is, again, work from Giovanni. We have tested the theoretical model that you can see here in this line. Again, these are void numbers as a function of size. And these are the measurement from a simulation. So you see it works pretty well. This is a lambda CDM simulation. We're just losing some counts here. We do not detect enough small voids in this simulation, given the resolution of the simulation. So dense surveys such as PFS or the Roman Space Telescope will target this part of the void size function. And then we have also tested the same model in the case of different dark energy prescriptions. And this is what you see here. The prediction for voids of different depths, this is what each line indicates, and then how it matches with what we observe in the simulation. And again, this is a simulations where we are considering halos and not dark matter. So we have talked about the void density profiles, so void shapes. We have talked about void numbers. The next step is to ask ourselves, aside from dark energy, can we constrain something else with voids? I mentioned the sensitivity to neutrinos. As a matter of fact, and this is work from Christina Kreisch here at Princeton, basically, we have looked at when we increase the mass of neutrinos, the number of voids will change. And this is basically the ratio of void numbers in the different cases here. But void numbers are not the only tool that we can use to constrain massive neutrinos with voids. It turns out that we have a new statistics that we can look at, and that is the void-void correlation function. So this basically gives you the probability. Say I take a random void center here. I want to ask, what is the probability to get another void center at a certain distance? And of course, it will peak at twice the median sample, the median radius of the void sample. And this is what you see here. This is the void autocorrelation function. And what we see is that aside from this peak, we are particularly sensitive to the properties of neutrinos. Typically, massive neutrinos will have a different void-void correlation function, and this can be detected in future data. Now, perfect, thanks. Now, just before concluding, I would like to highlight that because voids are large objects, we need to explore them with a huge set of simulations. And we have prepared very recently and released a couple of days ago in the archive a set of void catalogs that basically includes 15,000 void catalogs in lambda CDM cosmology and 7,000 different cosmologies. So jointly more than 1 billion voids spanning this set of parameters. Those, the Gigantes void catalog is built from the Quixote simulations. And it allows us to explore a bunch of properties for those voids. And one of the most interesting ones is the fact that voids are really complementary with other tools. And this is what you see here for a set of parameters. So this is omega m and the mass of the sum of the neutrino masses. And you see that we have the halo mass function, the void size function, the halo-halo correlation function, and the void autocorrelation function. And when we combine this, we get extremely tight constraints. And a combination is also particularly interesting for other parameters, of course. So I encourage you to check other plots that we have in the paper to explore this huge set of void catalogs that has also been constructed for the possibility of using machine learning to explore the cosmological information content that we have from voids. So here are my take-home messages. Void analysis is an active field of galaxy clustering. It already gives competitive supercent level constraints. In particular, the void galaxy cross-correlation function is already a robust tool for cosmology because the main systematic effect that we had, the velocities, have turned from being a systematic effect into becoming a source of information. So voids, in this sense, are leaving the realm of standard probes, and we can expect that most of the large collaborations looking at large-scale data will look into voids in upcoming years. I have highlighted today the importance of calibration-free techniques that do not rely on simulations. And I also have introduced the use of the void size function, so void numbers, that we are developing and that we are testing in order to soon lead to an application on data. I also have introduced the void-void autocorrelation function. That is a new promising tool to constrain cosmology. And I have mentioned that with upcoming surveys, TFS, DESI, Euclid, Rubin, Raman, and Spherix, we'll have the order of 10 to the 5 voids for each survey. So theory really needs to keep the pace with data if we want to exploit those voids. And thankfully, one of the ways to improve our understanding of theory is to use a huge set of voids from simulations, the Gigantes suite, that already shows the combined power of void statistics to constrain independently and in combination with other probes, the set of parameters that will allow us to better understand our universe. And I guess that's it. Thank you very much.
Thank you. Thank you, Alice. If is there a very quick question? Because we are already running a little bit late. If not, maybe we can keep all
Yes,
the
I've got
other...
a question. I've got a question.
Okay. Yeah.
I can. Yeah, thanks. Yes, thank you very much for this very interesting talk. Years ago, some teams worked with the Swiss cheese models to represent the local universe. And those teams showed that voids expand faster than the background, even without dark energy. What do you think about that?
So that's particularly interesting. I have to say, we know that voids expand, well, of course, because there is dark energy, but also generically because they have overdense boundaries. And so matter is just flowing towards those overdense boundaries. So I don't know if this contributes to the effect that you are considering, but it's very interesting. Do you have a reference I could look at for this? Oh, sorry.
You're muted.
Yes, I can give you many references, and I work on this field. Yes.
Okay. So then I'll just look at your papers on arXiv. I think so. I'm not an expert on Swiss cheese models, but
yes, it's an old work for me. I did that in the 2000s. Yeah. But you can have a look. It's interesting.
Okay.
Yeah. It's very interesting because we do consider that it's mostly dark energy that is driving this, but it's dark energy and the fact that voids can be considered as isolated universe, where cosmology is a little bit different. And so in this sense, they feel an attraction towards the edges that are overdense. So in this sense, you can think that even aside from dark energy, there could be an expansion that is faster than the background, but I will need definitely to think about this a little bit more.
And there are also other problems and issues with this. So
interesting. Okay, I will look at this and thanks. That's very, very helpful.
Okay, thank you.
Thank you.
Thank you, Alice. We can switch to the next speaker now, which is Jeremy Darling, which will talk us about cosmology with secular redshift drift. Thank you.
Can you hear me?
Yeah.
Okay, great. Well, thank you very much for inviting me to participate. And so I'll be talking about the secular redshift drift. I'll explain what that is in a moment. So here's our universe, of course, galaxies. And because astronomers live such short lives, we talk about the position of a galaxy and the redshift of a galaxy. But as we know, we live in a dynamic universe. And so if we could measure things very precisely or live very long lives, we would talk about the position or the redshift of a galaxy at a specific time instead of just as seen. So this is the idea behind real-time cosmology, is to make measurements or observations of a dynamic universe that changes over the span of years. And what I'll be focusing on today is the time rate of change of redshift, or the redshift drift. So we'll call that Z dot. And that's just the difference between a coasting universe, an empty universe, and the actual universe. So it's the difference between the Hubble constant scaled for the redshift and the Hubble constant at that redshift. But if we look at other observables in real-time cosmology, everything changes. So distances change if we wait long enough or we measure them precisely enough. Flux diminishes as the universe expands. Cosmic background pattern and temperature will decrease and change. So the idea here is, what if we could measure these quantities very precisely over many years? And what you'll see is that Hubble constant appears throughout, which really sets the order of magnitude size of the measurement you need to make. And it's roughly 10 to the minus 10 per year. So that's the rate of change of these observables, and it's usually less than that. So that's the threshold. So we need to make measurements that are better than parts per 10 billion per year. Okay, so speaking about Z dot, the radial acceleration, it's a direct measurement of the acceleration or deceleration due to a non-constant expansion. So a coasting universe is the only one that doesn't show a change in redshift over time. I'll show you the magnitude of this effect, but just note that gravitational accelerations are similar, about 1 centimeter per second per year. So that's the size of the acceleration that, in fact, the sun experiences as it orbits the center of our galaxy. And it's pretty typical of the motions of galaxies in clusters or due to large-scale structure. To measure this radial acceleration, the change of redshifts, any redshift indicator can be used. So we're really talking about spectral lines, but you could also think about doing this with the CMB temperature itself. Okay, so what does this look like? On the top panel shows Z dot, the rate of change of redshift. The bottom panel translates that into an acceleration in centimeters per second per year. And these are both plotted versus redshift. The blue curve is showing our fiducial cosmology. And you can see that we're talking about less than 1 centimeter per second per year in acceleration. So it's a tiny, tiny change. So we're talking about velocities changing by less than 1 centimeter per second per year. The takeaway here is twofold. One is that if we look at lower redshifts, we'll see an acceleration. We'll see redshifts increase. If we look at higher redshifts, we'll see a deceleration or redshifts decrease. And that deceleration is due to matter. And you can see in matter-only universes, we only see deceleration. Okay, so we only see redshifts decreasing. And it's when we add dark energy that we see redshifts accelerating or increasing. And so that's going to be really the focus here is if you can make the measurement at all, you can tell the difference between a universe that has dark energy and one that does not in a direct manner. So without using distance ladders or our geometry or standard candles or standard rulers. Okay, so here once again is the effect we're trying to measure, the difference between a coasting universe and the actual universe's expansion at a given redshift. And once again, the order of magnitude is very small. If we translate this into an acceleration, it's about 0.5 centimeter per second per year. What this really is us comparing or observing the redshift change over time. And remember that our time is passing as well. And so even though dark energy becomes dominant very recently, say redshift of 0.4, where we had this equivalence, we'll see an acceleration out to redshift of roughly 2.5. Okay, so if we talk about a flat lambda CDM cosmology, this measurement is most sensitive to the Hubble constant and to omega matter. So here is our equation for h of z, the Hubble constant, the Hubble expansion at a given redshift. And what is the effect of changing the Hubble constant? What it does is changes the amplitude of the signal. So a smaller Hubble constant reduces the size of the acceleration on both ends. So it just scales this, the amplitude of the signal, but it doesn't shift the signal left and right in redshift space. If we change omega matter, on the other hand, it both changes the amplitude and shifts the signal left and right. So that's this dotted line here. Okay, so omega matter changing by roughly 10% shifts our locus for the redshift drift. And so there's a degeneracy between the Hubble constant and omega matter in some ways because they both play with the amplitude of the signal. Okay, so I asked a question a few years ago about how low we can go, just to see how well we can do with this type of measurement. As I said, it's difficult, but it's no longer crazy. And what one needs, of course, are narrow spectral lines observed with high spectral resolution over a long period of time. And if you're going to compare observations spanning a long period of time, you need extremely stable calibration. And so this usually recommends absorption lines. Usually you would like to work in the radio. However, I'll show you examples of optical observations. But what you need is a very stable reference or stable calibration. And what that means is a local oscillator. So you need either an atomic clock or a laser comb for your calibration. You need very high spectral resolution, and you need to be patient, or you need to dig into archives and look into the past. But that brings up, once again, the stability problem. Okay, so I'm going to just show you what some data look like. Here's an example of 21 centimeter absorption toward a quasar. So we look at a gas cloud between a quasar and us, and we see this absorption line in the hydrogen spin flip transition of 21 centimeters. What one can do is dig through archives to see how far back we can observe these effects. And for example, for this particular object, we can get accelerations down to, say, tens of meters per second per year. Okay, so this is just a limit, but this is showing us how low we can go. And if we do this for about 10 objects, here is the outcome. We get down to a few meters per second per year uncertainty. So we're still not seeing either any signal, but we're also not seeing systematics. And I'd like to just stress how rather crazy these measurements are. So for example, this point here, the average redshift of this object as measured is 0.5237416, plus or minus 7. So we need this many digits plus 3 more to measure the cosmological redshift drift. Okay, so I need to add 3 digits to this sort of measurement to do this. So it's rather wild. Most folks who do galaxy surveys and observations might write down 3 or 4 digits. Okay, so that's the idea. This measurement has not been made. We're still a factor of 1,000 away from being able to measure it. However, so what I'm going to talk about now are facilities and transitions in the future where one can hope to apply this method. And there's been a lot of work on projections and forecasts for making the measurement. So first is the square kilometer array. This is a large radio array that has been begun. Its construction's been started. And there are two approaches here. One is the 21 centimeter absorption from galaxies, as I just discussed, but also one can think about using emission from galaxies. So either way, this will be large galaxy surveys, roughly 10 to the 7 objects per redshift bin. So a very large number of galaxies. This will be much smaller, in the thousands of galaxies or clouds. There are two facilities that exist today, FAST in China and CHIME in Canada. This is a H1 intensity mapping experiment, which can both in principle use the 21 centimeter absorption from hydrogen from galaxies to make the measurement. So we're not waiting on a new facility for these, but we will need a lot of time, decades. And then finally, extremely large optical telescopes can make the measurement from the Lyman alpha forests. This is once again neutral hydrogen, but using the Lyman alpha forest absorption from intergalactic clouds looking toward bright quasars. And what I'm going to show you is what these data look like now, the Lyman alpha forest. So here's a spectrum of a quasar at a redshift 2.6. This big bump on the right at 4,400 angstroms is the Lyman alpha emission from that quasar. And everything blueward of that, all of this stuff you see, this is not noise. Every one of these little dips is absorption from an intergalactic hydrogen cloud. Okay, so we're seeing hundreds of clouds between the quasar and us at a large range of redshifts. And here's a blow up of that region. This is a Keck spectrum. And you see every one of these little features is a different cloud. Here's the wavelength as observed. Here's the Lyman alpha redshift. Okay, so what these let us do is not probe a specific object or cloud, but a vast range of redshifts all at once. And so we can probe a big chunk of redshift space simultaneously. And then if we have multiple epochs, we can overlay these like so and compare them. And so what I'm doing is doing basically looking at this comb of lines and watching it shift over time. And that's how the Lyman alpha forest works. So if we combine all of these things, I'm looking at both 21 centimeter emission, 21 centimeter absorption, and the Lyman alpha forest. This is a forecast for our ability to measure the signal. Here's acceleration in centimeters per second per year versus redshift. So these error bars are showing the uncertainties in measurements predicted for absorption line measurements. This band here in orange is for 21 centimeter emission. And this band in green is for the Lyman alpha forest from the ground. And then we see our various cosmologies in here. And I want to point out that the uncertainties in most of these measurements are of the same order as the family of cosmologies that I've placed on this plot. Okay, so we're not going to be doing precision cosmology with this method. But I'll get to that in a moment. So if we, for example, look at the 21 centimeter emission prediction as detected by the square kilometer array, that goes up to around a redshift of 1. And so what would be seen there are, as we watch redshifts, we would see the redshifts increase. So we'd see an acceleration. So the acceleration regime would be measured by 21 centimeter emission. If we look at 21 centimeter absorption, we go up to redshift 2.5. And this, once again, is still the acceleration regime, but we would cover the entire acceleration regime. So with 21 centimeter observations, both emission and absorption, we can pretty much continuously cover from redshift 0 to 2.5 and cover the full span of the acceleration part of the signal. And now if we look at the Lyman alpha forest absorption, this starts around a redshift of 2 and runs out as far out as one can find quasars and gas clouds, which is roughly redshift of 5. And you'll see that this is all in the deceleration regime. Okay, so we'd be measuring deceleration. But I want to stress that this deceleration, if one can make a measurement out here, is very different from this green line, which is the matter-only universe. So although you only see deceleration with the Lyman alpha forest, it's still a very different value than one would measure from a matter-only universe. So you could still infer, for example, the presence of dark energy directly. Okay, so any measurement tests dark energy. So even if not all of these predictions come to pass, if one can make any single measurement here that is non-zero, It is a direct measurement of both the expansion evolution of the universe, the acceleration or deceleration, which tells us instantly, basically is direct evidence that dark energy is present without using a cosmological model or distance ladder or standard candles or standard rulers. Okay, so of course we're very worried about systematics. That's going to be what people worry about the most with this sort of approach. So we're very much worried about calibration and stability. Gravitational acceleration, as I said, is a similar signal. So it's about 1 centimeter per second per year for many objects. And so what will save us from gravitational acceleration clobbering the signal, which is actually smaller than this, is that gravitational acceleration will have a random sign, whereas we have an expected sign, acceleration or deceleration at a given redshift. So this will basically add noise to our ability to make the measurement. And so what this will do is drive observations to use longer time baselines and more objects in order to beat this down. So that said, intergalactic medium measurements are favored over galaxies because peculiar accelerations for intergalactic medium clouds are expected to be smaller than, say, motions of clouds in or around galaxies or in clusters. So the Lyman alpha forest is in some ways favored for systematics if one can obtain the calibration and stability that one needs. But the other thing, of course, for systematics is that multiple methods are important. Okay, so the last thing I'll do is make some forecasts for cosmological parameter measurements from the data or predictions that I showed you for the measurements themselves. And just to remind you, this is what we're measuring, Z dot, which depends on the Hubble constant, omega matter, omega lambda, and curvature. And so there's dark energy contribution. If we assume a flat line of CDM, that's what I'll show you first. We're measuring the Hubble constant, omega matter, roughly to plus or minus 2%. If all of those measurements are made and we use them, we fold them all in. Of course, these are highly correlated. As I said, both influence the amplitude of the signal. If I expand the possibilities or the number of parameters in the model and we allow for a different form of dark energy using, say, W naught WA, then of course my uncertainties get much larger and they're all highly correlated. So this technique is not going to be terribly profound in terms of constraining dark energy parameters. Okay, we're looking at plus or minus 0.1 in W naught. But what it will do is give us a direct indication of the changing expansion rate of the universe. It will be a real-time measurement of a dynamic universe. And we can, any non-zero measurement can easily infer the presence of dark energy independent of any sort of distance ladder, standard candles, or standard ruler. And that's it. Thank you very much.
Thank you. Thank you very much, Jeremy. If there is a question. If not, maybe we can postpone possibly the other question to the discussion part, and we can continue with Simon Birrer, which will talk us about time delay cosmography, present and future.
Yeah, thanks very much for the invitation, and it's my great pleasure to talk in this 20 minutes about the present and future of time delay cosmography. It has attracted quite some attention in the past and recently in measuring the Hubble constant. And here I want to, the first part, introduce the measurements, the methodology, where we are now, and then in the second part, look in the future. What will we have accessible in the near future? How does this methodology work? So it's basically we see images multiple times on the sky, and if in a strong lensing system, so you have a massive, in that case, a foreground galaxy, can also be a cluster or any other massive object, and if this object behind what we call the source is variable, we can measure a time delay between the time a photon travels through the universe to reach our detector. Here, in that case, the Hubble Space Telescope. And this time delay is caused by the gravitational potential it passes through, and the geometric path difference between, in that case, these two paths. And depending on the configuration, whether the universe is smaller or larger, these expected time delay scales up and down, linear with the scales of the universe. And so if we can now measure a time delay, and knowing the relative geometry of the paths, and this is basically the formula for the predicted time delay, this is optical quantities and knowing differences in the paths and in angles on the sky. And this is an absolute scale in the universe, which scales. So we can turn that around and say we know, or we get an estimate of the geometric portions. We can measure an absolute time delay with a clock and the observation log on Earth. We can turn it around and measure this distance. So this is it for like an elevator pitch. What can we then do with the distances we obtain? That's hence the name cosmography. This distance, or any absolute distance in the universe, is effectively inversely proportional to the Hubble constant modulo the relative expansion history. And by what we say, by measuring the Hubble constant, we effectively determine distances and then turning into what we expect that late or at redshift 0 to be. What do we require for this measurement? First of all, measurement of relative time delays between images, and then the estimating of the Fermat potential. So this is this term here in the second part. And for this measure estimation, we need a main deflector mass profile. So what is the main contribution to the lensing? And line of sight convergence and shear contribution. So everything along the line of sight contributes to lensing to some degree, and that we need to take into account. Here an illustration of almost a decade-long observations, a series of observations to measure the time delay. And with monitoring, basically nightly cadences, and you may see by eye, you can shift the curves by a certain amount of days or fractions of the day to match and to measure the time delay. The correlated signal is effectively the time delay component, and there's uncorrelated ones that is also like microlensing and other parts, which I'm not going into detail. So that's on the time delay side. What can we learn about the lensing distortions that we see on the sky, and then in particular the Fermat potential? Basically, that's the problem we're facing in brief. So we have some source that's being distorted, and then we have aperture effect, convolution, seeing, pixelization, and noise. And when we see something on the sky like this, we want to go back and say, okay, what is the lensing quantity fit? Not going into the detail of all that, but effectively what we're using is forward modeling on the pixel level of HSD imaging. Here, just one example. This is from Shachi et al. that co-supervised. To just give you an idea of the complexity we put into the models to derive these relative distortion quantities that we're using. Another quantity we need is the line of sight contribution, so the external convergence. So we need to know, is the sight line we're looking actually perturbed relative to the cosmological background? And the answer is all sight lines are slightly perturbed. And the question is, in what direction? Is it more overdense? Is it underdense? How close are the nearest perturber? Do they give higher order lensing terms? And that's aspects we need to quantify statistically to see what we're actually looking at. And we expect lenses to have a certain selection bias on the sky, and we need to take that into account. This is the overview where the Holy Cow collaboration was something like now getting 2 years ago, where the team analyzed 7 lenses, here presented 6 lenses with certain assumptions on the mass profiles, and assumed that they're independent, and then combine those and get a precise measurement of something like 2.4% on H0, consistent with a Schuss team's measurement. there's an important caveat to this part, and that is known since a while, since decades, and this is the mass sheet degeneracy. So what effectively this statement, this mathematical statement means is, no matter how good your lensing distortion observables is, there is insufficient amount of information to distinguish in that case between 3D density profiles that are scaled by this transform. And the scaling of the transform to make effectively the profile more fluffy or more cuspy can scale up the Hubble constant inference. So the same predicted data only changes effectively the time delays. And so if we get the wrong time delay predictions, we get the wrong Hubble constant. So the question is, what kind of assumptions are we allowed to make? What is physical? What is reasonable in that regime? And what other data we have to actually learn about these quantities? And we do have data to learn about. And one of those that we are now currently using is spectroscopic data for measuring kinematics, so the orbits of stars in the potential of the main deflector. So this is integrated, so this is velocity dispersion measurements, is not individual stars, but this gives us an independent kinematic tracer. And in terms of that lambda parameter, which is this mathematically of scaling it, here you have the prediction how the time delay changes, and thus the Hubble constant if you're using it. And luckily, it also changes the velocity dispersion prediction. And so if we have that other anchor, we can actually learn from each other. There now, the velocity dispersion has some other distances involved, a ratio. It's not an absolute scale in the way that we observe it, but this is the tools that we have. And when combining now, allowing a full freedom in this additional term, being very relaxed on what actually the assumptions are on the density profile, folding in the information of the kinematic, and doing the two-dimensional inferences of these distances and distance ratios, while the time delay gives us the absolute distance anchor, we can do a joint inference of this. The key in this work here is not to have one lens or two lenses, but we actually need dozens of lenses. So in the joint combination, we have 7 time delay lenses and additional 33 lenses with only kinematics and lensing, but those can also provide us valuable information on the density profile on the ensemble level. And that's how we here perform the hierarchical analysis of H0, by jointly constraining galaxy density profiles and stellar anisotropy to marginalize over. So our key systematics in that regard. So that brings us to the current status, which this is the holy cow result of Wong et al. And then what we did in TD Cosmo 1 is splitting. We have put into 2 assumptions in the mass profiles in the holy cow collaboration. One is a single power law, and the other is what we call a composite, which is a fixed mass to light ratio scaled with an NFW profile on top that has some priors on mass concentration and mass relation. Both assumptions here in that case, how it's been used to give consistent result. But when we now relax the assumption and only operate on the 7 lenses, we see we get about an 8% measurement. And here's purely we anchor it on kinematics. And when we add additional external data sets about knowledge about the density profiles of galaxies that happen to be lenses, we can shrink the error bars. And in that case, with this black sample, it shifted consistently within the expectations of the measurement uncertainty. And that's what we are currently on. And some people may wonder, here's just another slide of the interpretation, what this means in terms of the mass profile. In the work of TD Cosmo 4 that just presented, there was not like a physical interpretation of what these mass profiles actually look like. So we just do this transform. In Shashib et al., basically using the same data, we can either relax the assumption on the constant mass to light ratio, so having a gradient therein, slightly halo responses in contraction and expansion of the density profile, And in that sense, just if you're interested in dark matter science, this may also be very valuable information to learn about the distribution at the same time, as we require effectively the same data. This is then the overview figure. It depends on what assumptions you want to go. And I know different people in collaboration have different preferences. In that sense, here's just the schematics of what data you want. What I have to add here is we did the analysis, all of them basically blind. So we choose a certain methodology, we choose the type of data, and only then see where these things lie. And that's how we're continuing as well. So what is the future? So some people may have been, I don't know whether disappointed was the right word, but definitely a bit surprised depending on how results were moving in both the mean value and the precision. And one aspects I really point out of the model, how we revamped the analysis, is it allows us to include on the likelihood level, so on the data level, a lot of additional data that we previously was not being able. And we have just started about that with very few. So we talk about 33 external lenses and 7 time delay lenses, while the next decade allows us to incorporate hundreds or even thousands of additional lenses and data sets, as well as more precise kinematics and other data sets to do it. So in that sense, it's really only the beginning of the way we expect to do the analysis in the future. So that's effectively my main key point in that sense, where we are now, where we are going to be. Give you a bit of an idea, this is a sample of 12 lenses that have been discovered in current surveys and have already been followed up, in that case with Hubble Space Telescope. And not only that, we have already here preliminary models for those that we're going more industrial towards the analysis. And we can expect that more and more of those lenses, if we get the time delay measurement, etc., that we can produce this type of analysis. One key part in the near future and what we actively work on is spatially resolved stellar kinematics measurements. So we really rely on lensing independent information to pin down the major systematics that we currently have, or uncertainty depends on way how you treat it in our measurement. And so the focus currently is on getting spectroscopic data. This can be from ground-based adaptive optics, such as IRIS, KCWI on Keck, or MUSE on the VLT. We have an approved JWST proposal for one lens that gives us exquisite data. And then we were also working towards and very excited about ELTs in many regards, and in particular also spatially resolved kinematics. And the forecast here, I perform basically on the same methodology that we previously applied on how well we can measure the Hubble constant. It basically goes to about 1.5%, with also some uncertainty actually being the relative expansion history at that level of the uncertainty that kicks in, that we also need to control, or having external data set. So another aspects that comes up that is lens supernovae. So currently the methodology has primarily been applied to lens quasar. They're bright, and you don't need like transient surveys to discover them, but with CTF, PTF, and in the upcoming LSST, we expect a lot of these transients to be found, discovered, and with the follow-up capabilities to actually measure time delays and getting the highly resolved data. One thing is supernova ref style. This is on a cluster. There's also a talk, I'm not sure, Massimo Meneghetti gave a talk, or Claudio Grillo, on the supernova ref style on a cluster. I'm very excited to see the results coming out of this as well. And this is the first lens IPTF 16GU. It's the first lens discovered on galaxy scales. They have some advantages. One is they have a characteristic light curve. They're not like damped random walks like quasars or whatever the chaotic description is. It's very characteristic, and thus measuring time delays these characteristics can be used to measure actually time delays precisely. And the supernova fades away, and when it's faded away, it's easier to do other follow-ups, such as stellar kinematics, for example. Don't have to deal with a super bright quasars that contaminates your light. And the last bit I'm also particularly excited is standardizable magnification. So what does this mean? This means effectively when we have the difference between how something appears on the sky when it's lensed or when it's not lensed, the difference is effectively the magnification that lensing is called. If we know how an object actually looks intrinsically or unlensed, we can make use of this lensing magnification to break the Mashy degeneracy, so the dominant uncertainty. And so we can actually use these lens supernova standardizable magnification. We don't need an absolute bolometric luminosity. We just need to know how they look as apparent unlensed on the sky. And here's the forecast we bring out hopefully in the next few weeks together with Suhail and Anwar, where we do the forecast of what LSST will bring us. And the big question mark is on microlensing, to what level it actually affects. And
2 minutes.
now I'll go just quickly, we're also exploring how we can actually deal with thousands of lenses. We may need to change certain approaches. One way is using hierarchy or Bayesian neural networks and then perform the entire hierarchy in this with such neural network. Here also the software is open source, and here's some paper that I co-supervised of 2 graduate students at Stanford within LSST desk. Then another thing, second to last slide, open source software. So all the analysis needs to be very robust, tested, and having the software publicly enables both other people to actually take on and maybe do things differently. The analysis of TD Cosmo 4 is fully publicly available, so you can even tweak and change them. And it results also in a quality control and generally better development of the analysis we're doing here as an example. And so the conclusion in here is that we expect a fast increase in the sample size of both lens quasars, lens supernovae, non-time delay lenses, and there may be other lens gravitational wave, lens Fermi, radio burst, etc. So that the sky will be full of strong lensing effects in the transient domain. We expect improvement of the kinematic data quality to what we currently are using, both spatially resolved, systematics in the calibration, being better in actually measuring the velocity dispersion, etc. And the focus also on the systematics. So the current most dominant systematics or uncertainties are related to density profiles of strong lenses and selection effects. So if you have different samples in the future, we have to understand their selection functions relative to the background density, so to speak, orientations we're looking at, and so on. And general message, I think that's for all probes in general, new and old one, the same, challenge yourself. So improve simulation products for validation and methodology. We have done also like a blind analysis challenging on the imaging data, was very fruitful of learning aspects, and keep the analysis blind. So these are important questions we're hunting to, and it's very, well, unconscious biases may be there. And so it's not comfortable to do it blind, but it's the right way to go. And open source, putting the analysis out to see how we as a community can learn and make things more robust. And that's it from my side. So thank you very much.
Thank you. Thank you very much, Simon. Very nice talk. Is there a question for Simon?
Yes, thanks for the talk. I have a question. So if there is any correlation or sensitivity between the time delays, or finally the cosmological parameters, and the redshift range of the lens and the source?
That's a good question. So there was a 1.9 sigma correlation in this diagram, basically, that certain lenses at higher redshift measured a slightly lower H0 than lower of 1.9. This is under these assumptions here. and so if you relax these assumptions, go into the density profiles, relax those, we don't have the ability within the uncertainties to actually quote a correlation. Or these, if you trust these assumptions that may or may not be valid on the density profile, then you see a 1.9 sigma correlation. Once you relax these assumptions, there may be more like a correlation in the density profile, depends on what angle you're actually measuring the mass density, what type of galaxy evolution is being caused between the redshifts. And so selection effect and constraints of an evolving galaxy population over redshift is one of the systematics before, and that I would look into more details before claiming that actually the Hubble constant is evolving differently than within lambda CDM.
Okay, thanks so much. I see. I understand now. Thanks.
Thank you. And now I think I will leave the chair to Lorenzo for the second part of this parallel session.
Yes, good afternoon to everybody. So I guess, Michele, we are not having the break, or if you wish just to take a minute of relax, we can take a 5 minutes break, so we can reconvene at 6:10, and then we go on with other talks. Fine, Michele, for you? Okay.
Yeah,
so
fine.
Thank you, and let's get in touch within 5 minutes. Thank you. Hello, so welcome back to this last part of the last session of this parallel session on non-standard cosmological probes. So now I invite the next speaker, Joseph Purvilla, to share his presentation, and he will present to us constraining neutrino mass using 3-point mass relative velocity statistics.
Can you hear
Joseph,
me?
thank you. Yeah, perfect.
Okay,
perfect. Thank you.
Yeah. Okay. Good afternoon, all. Thank you to the organizers for having me here. So today I'll be talking to you about constraining neutrino mass using 3-point mean relative velocity statistics. So this is a work I've done here in University Paris-Saclay with Nabila Aghanim. You can find the reference as mentioned here. So just to give you the current rundown on constraints on the some neutrino mass, if you look into the terrestrial experiments like the Katrine, as reported the first detection of sub-EV neutrino mass with an upper limit of 0.8 EV. However, while if you look into cosmological probes by combining CMB, BAOs, and redshift-space galaxy clustering, one can obtain much tighter constraints of about 0.01 or 2. However, the cosmological constraints on neutrino mass is model dependent. And if you were to consider extensions of standard cosmological model, the current upper limit on the neutrino mass from cosmology becomes less stringent. And as you saw earlier, like most of the constraints has been done from the clustering analysis, for example. So one can ask, if not using for density and one were to use a velocity information, is it possible to constrain neutrino mass? Because it should in principle provide an auxiliary information. So here the velocity statistics we consider is the pairwise velocity, whereby we consider the velocity separation. Here we consider two objects, 1 and 2, as shown here in this illustration. And the velocity vector is given by the blue arrow as one sees. And one can do the radial velocity pairwise velocity difference by projecting it along the pair separation. So as shown in the equation. And if one were to compute the mean of this velocity statistics in the single stream regime in cosmology, one can, in the single fluid regime, one can write it like this. And using leading order in perturbation theory, one gets it as an integral of the power spectrum with the time some Bessel function in principle. So this is, at least on the linear scales, it's a well-defined estimate. And this has been not only been used to for different matters, but this also led to the first significant detection of the kinematic Sunyaev-Seldovich effect. So whereby a proxy for the mean pairwise velocity was used, as shown in the equation on the right. So the temperatural difference one measures from KSE, a pairwise measurement is basically tau weighted the pairwise velocity. And on the plot, which from the Nikan shows the first significant detection of KSE, and one sees that on the as a function of separation on the x-axis, and you see the pairwise velocity or the momentum here on the y-axis. And the reason why this is negative on the smaller scales is implying that the pairs are infalling towards each other on average at smaller scales. This is understandable as the separation between 2 points decrease, the gravitational force dominates and causing more and more on average to fall towards each other, basically. So that's the like a simple intuition behind this summary statistics. And this pairwise velocity measurement from KST has been also shown to be a novel probe of some neutrino mass, and by Eva Müller in 2015. And we studied the impact of massive neutrinos and its interplay with baryonic physics also in a recent paper last year. However, the question I want to ask here is that in the clustering regime, for example, one now goes to beyond the power spectrum to constrain a three-point correlation function or the bispectrum in Fourier space. Can we do something similar for the relative velocity statistic and generalize it to 3-point? And this was done also last year, in May of last year. And just to show illustratively, it amounts to adding a third point and as such becoming a triplet. So instead of one pairwise velocity here, you have two relative velocities so between pairs in this triplet, basically. So what I call as R12 and R23. And again, the implications are the same, whereby the velocity difference is projected along the pair separation in 1,2 or 2,3. One can also measure, of course, the 3-1 also, but this forms a redundant information in the sense that you have the triangular constraint. So if you know the 1 and 2, the pairwise velocity vector, one can automatically constrain the third. Hence, one only need the two relative velocities here. And the question now comes, pairwise velocity itself was shown to have a novel probe of neutrino mass. Can we do the similar for the 3-point and use this to constrain cosmology? So here, for this purpose, we started with a Fisher matrix formalism to understand what's the information content in not just in the 2-point relative velocity statistics, but also to the higher order, which is the 3-point mean relative velocity statistics. So for this purpose, we use the Quixote simulations with the box length of 1 gigaparsec and number of particles of 512Q. So the good thing is that the fiducial simulation with the Planck 2018 cosmology close to it provides 15,000 realizations as shown in the first line of this table taken from Han et al. So this is good for creating covariance matrices, but also additionally, the Quixote suite of simulation provides simulations where you change the value of the cosmological parameter one by one, which one can use to compute the derivatives as partial differentials one requires in the Fisher information matrix. So in the case of all the parameters except for neutrino mass, one can use the equation on the left-hand side, that is just the increment and the decrement minus 2 dt. And in the case of a neutrino mass, because the fiducial value itself is at 0, we use this formula, but that's just for the information here. And then we can play the game where the Fisher matrix, the components of the Fisher matrix are directly computed from the simulation itself. That is, the covariance matrix and the derivatives are computed directly from the Quixote. And just to give a quick rundown on the Quixote suite of simulation, it provides you 44,100 full n-body simulations. And the good thing is this work runs parallel to the information content quantification of the halo bispectrum and the power spectrum from Han et al. In 2020. So here we consider triangular configurations from a minimum pair separation of 50 to 128 inverse megaparsec. And we wanted to create somewhat mimic the cluster scale cluster masses. So we here took groups of clusters, that is, we consider minimum halo mass from 5 times 10 to the 13. And then using the 15,000 simulations, for the left plot is basically showing you the first mean relative velocity in component, and on the right is the R23. So these are just basically the two relative velocity statistics between pairs in a triplet. And basically the blue line in the measurement, solid line, which denotes the direct measurement from the simulation, while the dashed orange denotes the leading order perturbation theory prescription. So one can see at this quasi-linear scales, we can do relatively straightforward. So just as in the case of 2 point, one can write it down in the single stream regime, and one can write it as a sum of mean pairwise velocity components. So one gets in the end that the formulation is that the R123 is obtained as a sum of different pieces of the pairwise components itself with some geometric terms. And this prediction is accurate, as one can see in the residual plots in the bottom, to about 5% at these scales. And for most configurations at the larger scale, one can see that this is more and more close to less than 1 to 2% basically. So which is quite good to show that, okay, first of all, our theory we can do at quasi-linear scales. Of course, to push it to non-linear scale would be difficult. Hence, it motivates us to use the Quixote simulation directly. So we can push the analysis to non-linear scales, and also shows the correctness of our measurement. And then we can compute the effect of massive neutrinos. So on the y-axis is we fix a leg of the triangle, like we have 3 legs of the triangle where we fix one, that is the R12, to this 115 to 128 inverse megaparsec bin. And on the y-axis, we vary the R23, but scale with R12. And on the x-axis, we vary the R31. So we can kind of do like fixing on one leg of the triangle. We look at how the effect of neutrino mass affects the summary statistics in this case of mean pairwise velocity, mean relative velocity between pairs in a triplet. So talking about effects of neutrino mass is a bit more complicated, because here we fix sigma 8 rather than AS. So one sees the effect of, by increasing the neutrino mass, we are increasing the amplitude of the summary statistics, especially at the scales of equilateral triangle, that is on the right most of these 3 panels. The squeeze we are not considering because we did a cut of minimum pair separations of 20 megaparsec. And this similarly, one can check it for different parameters where we increase and decrease the omega m in the first row, omega b, and h, ns, and sigma 8 subsequently. So just wanted to show here quickly that the effect of the different summaries, the cosmological parameter on the summary statistics is about 5%, it's 6% on different scales. This is again looking at a very small subset of triangular configurations. And hence it looks like one can go ahead and constrain the information content. So as I mentioned before, we use the Fisher matrix formalism, whereby we need the derivative and the covariance inverse of the covariance matrix, both of which we compute directly from the simulations. And for this purpose, we consider all triangular configurations from 20 megaparsec to 120 megaparsec, basically. So the different cosmological parameters as shown in the plot, with also B, which is the biasing parameter we show here. So the blue line the blue contours correspond to the mean pairwise velocity, and the darker shade corresponds to the 1 sigma, and the lighter shade corresponds to the 2 sigma contours. So one can see the constraints from the mean pairwise, while on the orange is given, it gives you the 3-point mean relative velocity statistics. So for all cosmological parameters, you can see this is a quite substantial gain. For example, omega b and omega m, this is about 8 to 10 times better constraints on both parameters. But for ns, it's also quite substantial with about 20 times better constraints. And looking especially on the neutrino mass, one can see from the pairwise, the 1 sigma constraint from the pairwise measurement itself is about 0.87 eV, while from the 3 point, it comes to about 0.065 for EV, right? So this is telling us that the constraints or the information content from the 3-point mean relative velocity statistics is quite high, and this could be a good probe for in the future. However, we started with the conversation that, okay, density field provides us the stronger constraint, but it's fair to ask now, is this really competitive with the clustering statistics, right? So far mentioned, okay, how it works better than the 2-point case, but is it competitive with the galaxy clustering statistics? So here, then we compared it with the Changbong Han paper or the work where they consider similar halo mass and also similar scales where they do a similar analysis whereby choosing halos from Quixote simulation and with the mass of 3.2 times 10 to the 13 and above, and of 2K max of 0.5. So really pushing it to nonlinear scale. So on the second line, that is the mean relative velocity, we show our 1 sigma constraint on the different parameters, that the matter density, baryon density, H spectral index, sigma 8, and some neutrino mass. And in the orange box, we show the number within the orange box, the factor of improvement of 1 sigma constraint from our summary, the velocity statistics over the corresponding clustering statistics. So in the power spectrum multiple, one can see that, for example, if one were to focus on the some neutrino mass, the 3-point mean relative velocity statistics provides a better constraint by 4.5 times than what one can achieve in the power spectrum multipoles. And this also, one can see, corresponds, goes over to other parameters, especially, for example, the Hubble parameters with a improvement of factor of 4.9 or so. A more fairer comparison with respect to the clustering statistics would be to compare it with bispectral monopole, which is the 3-point clustering information in Fourier space, just the monopole here. So one can see that with respect to sigma 8 and neutrino mass, there is a slight reduction in the improvement, that is 0.9 and 0.8, while on the other parameters, that is the matter density, baryon density, Hubble parameter, and spectral index, it's a mild to moderate improvement with respect to bispectrum. So this tells us that the 3-point mean relative velocity statistics provides us a improvement of, it's quite competitive when compared to the 2-point, not just to the 2-point velocity statistics, but also to the 2-point clustering statistics. So with this, I would like to conclude. So just 2 quick takeaway points from this talk is that the leading order perturbation theory prescription for the 3-point mean relative velocity statistics works quite well on quasi-linear scales and above when compared against the direct measurement from simulations, where we have considered about 15,000 fiducial realizations here. But also, more importantly, the cosmological constraints from the mean 3-point relative velocity statistics is quite competitive with those obtained from bispectrum, but also having a substantial improvement with respect to the power spectrum. Yeah, thank you for listening.
Thank you very much, Joseph, for the nice talk. So there is thank you also for being very on time. So there is some time for possible questions, if any, from the audience. Please, of course, feel free and relaxed and pose questions. Or, of course, you can then contact Joseph offline, or send questions to him. Okay, so if there are no questions, I thank again very much our speaker. Thank you so much. And so now we switch to the next speaker, which is Tony Bonaire, talking about constraining cosmological parameters with cosmic environments. So thank you, Tony. You can share your screen.
Hello, can you hear me well? Oops.
Yes.
Can you hear me? No?
You are very weak.
Oh.
Your voice is very weak.
Okay. I thought it was fixed.
It's improving.
Maybe I need to hold the microphone like that. Is that better?
Yeah, this is marginally detectable, but yes, now you are detectable.
Oh, I'm sorry for that.
Would say 2 sigma detection.
You want me to? Okay, up. It's not better, no?
You are very, very weak.
Okay, I'm sorry for that. Should you move to, I don't know what to do.
No, but you can go on like this. We can
Okay.
pump up the volume. Yes.
Okay. So yeah, so thank you first for the letting me presenting my work on constraining cosmological parameters with cosmic environments, which is a collaborative work I've been doing with Joseph Kuruvilla, who just presented his work, Nabila Aghanim, and Aurélien Decel. So I'm a PhD student from the Institut d'Astrophysique Spatiale in Orsay in France. And first, let me give you a bit of an introduction of what is the cosmic web and what are the cosmic environments. So initially, the matter distribution in the universe is assumed and observed to be nearly Gaussians with small perturbations that evolve through gravity and time to what is observed today, for instance, in the galaxy distribution of the Sloan Digital Sky Survey here. And on the right panel, the dark matter density field of some simulation, like the Illustris simulation here. So in this picture, you have massive nodes that are anchors of the cosmic web that are linked together by elongated bridges of filaments of matter that we call filaments that themselves are found at the intersections between mildly dense sheet-like structures that we call walls that themselves are enclosing some nearly empty areas in the galaxy distribution and under dense regions in the dark matter density field that we call voids. And these structures are appearing depending on the axis of contraction of the initial spherical perturbation. So isotropically, it leads to a node. In 2 dimension, you have a filament, and in only one, it leads to a wall. So we know that these environments are really interesting already. Some of them are used to break some key degeneracies when using the matter power spectrum, for instance. For instance, massive nodes, clusters of galaxies are used through their counts, shapes, etc. to break degeneracies in the omega m sigma 8 plane, while voids, as Alice Pisani already presented earlier today, are very interesting for the study of dark energy, but also to probe alternative models of gravity. And it has been shown also recently to be a nice way to constrain neutrino mass. So for instance, here on the left, I'm showing the void abundance sensitivity of the to neutrino mass of voids, so from the paper from Kresh et al. 2019, in which you see that when you increase the sum neutrino mass in simulations, you have more voids of small radii. And you can combine this information obtained from the low density and high density environments. Here, for instance, this is what has been done by Bayer et al. 2021, in which they are combining the information of the halo mass function and the void size function, and you see that it leads to some orthogonal constraints in some planes of the cosmological parameters, especially in the mu sigma 8 plane, where you see, for instance, that the two information is really complementary and leads to improvement over the usually used matter power spectrum for that. So this was done in real spacing really recently, yesterday maybe, the day before. A paper came out using the halo distribution of the same simulation. So the question we wanted to ask with this work was, what is the theoretical cosmological information that is contained in these different cosmic environments? And stating it a bit differently, when I mean theoretical, I mean that we want to probe both linear and nonlinear scales, so we are using simulations. When I say cosmological informations, it means that we want to constrain cosmological parameters and compare it to the obtained ones with the matter power spectrum. And when I say cosmic environments, it means that we need to have access to a definition for the different environments and a summary statistics for all of them, which will be, in our case, the power spectrum in each environment. So to do that, we have been using the suite of Quixote simulations that Joseph already presented just before, so I won't be long on that. So it's a very large suite of simulations with more than 40,000 simulations spanning more than 1,000 cosmological models with a fiducial cosmology that is consistent with the Plan 15 cosmology, and then they are varying individually some set of cosmological parameters. And in our analysis, we have been using the matter and baryon densities, little h, ns, sigma 8, and the summed neutrino mass. So we want also to assess the information that we get in the different environments in both real and redshift spaces. So we simulate redshift space distortions in all the boxes of the Kyoto simulation to see the improvement over the real space matter power spectrum and the combination of monopoles and quadrupoles, for instance, in the redshift space. So the first thing we want to do when we have the dark matter particles from a Kyoto simulation is to tag dark matter particles as belonging to one of the different environments to then extract our summary statistics. And for that purpose, there are a lot of methods that have been developed these past decades with, for instance, Nexus Plus to detect the environments, T-Web, Disperse to detect filaments, VIT for voids, etc. So there are a lot of methods. Here we are using the T-Web classification algorithm, which rely on the gravitational potential and gives physical definitions for the environments that we will just see. So starting from the dark matter particles, the first thing we do is to estimate the overdensity field, delta, on a grid of 360 cube cells. And this is done through a B-spline interpolation of order 4, which is the piecewise cubic spline interpolation. And then from this density field, we can solve the Poisson equation over the discrete grid using an approximation for the Laplace operator in Fourier space, and it gives the reduced potential gravitational gravitational potential that I'm showing here, for instance. And from there, the T-Web formalism is telling you how to classify the cells in different environments depending on the eigenvalues of the tidal tensor, which is the Hessian matrix of the gravitational potential. And basically, it tells you that voids are a region of the space where the gravitational force is locally expanding, so with 3 eigenvalues that are below a given threshold. Walls are only 2, filaments are 1, and nodes are a region of the space where you have where you are locally contracting in terms of gravitational force, so 3 eigenvalues that are below a threshold. So this threshold is usually user-defined, and in our analysis here we use it as a nuisance parameter to assess the impact of to assess the robustness of the results that we provide with respect to change in this parameter, and also indirectly in the definitions of in the uncertainty that we can have on the definitions of the environment, depending on the definition algorithm that you use or stuff like that. So here I'm showing, for instance, a slice on which you have the different environments at the cell level that you can propagate then at the particles level to have to compute the overdensity field in the different environments. So for instance, on the top, you have the matter density field from which you can compute the matter power spectrum. And here I have been computing, for instance, the overdensity field from dark matter particles that reside in voids only, in walls, in filaments, and in nodes. So these will be our summary statistics, and we want to see how they compare each other and how their combination of the different environment is comparing to the overall matter power spectrum analysis. So the first thing we can do with these spectra is just to plot them. Here I'm showing them in real space on the left, for instance. So these are normalized spectra, which means that we see the contribution of each individual environment with respect to the matter power spectrum that is in black. And we see that filaments, for instance, is the dominating component in terms of power at large scales, while in small scales you see that these are nodes, and then comes in terms of amplitude, walls, and then voids. So the gray shaded area here are the bins of K that we do not use in the analysis that are above our K max of 0.5 H per megaparsec. And each spectrum that you see is the average of 7,000 realization in real space in this case. So on the right, I'm comparing the real space and redshift space monopoles. So in plain line, you have the same as on the left, yes. Which is the average spectrum for the real space matter power spectrum in black. And the redshift space counterpart, monopole counterpart, is in dashed line. So you see, for instance, that there is this dumping of power at small scales, which is due to the finger of God's effect that is creating some distortions in the pattern where clustered regions appear really elongated in the line of sight direction, and that is decreasing the power at this scale. So you see that this is mostly affecting, for instance, the node statistics, which, as we can expect, is really sensitive to that particular feature. And we also see it, for instance, in filaments and nodes and walls to a lesser extent. For voids, you see a global shift of the matter of the power spectrum. And the idea behind showing that is just to see that the different spectra in environments are showing different shape dependencies. And since on environments we know are probing different kinds of densities, density range and all, we expect different behavior for this their matter composition and hence their power spectrum when you are varying individually cosmological parameters. So this is what we have been doing. For instance, here when by showing the differences that you have when you are varying the sum neutrino mass, sigma 8 and omega m on the redshift space monopoles. So on the left you have the monopole from the matter monopole, the residuals, so which are the ratio between the spectrum that you get when you're varying the cosmological parameter over the fiducial 1 minus 1. So it's known that in redshift space, massive neutrinos can be effect on the matter power spectrum can be well mimicked by a reduction of sigma 8, for instance, in Villa-Escusa-Navarro 2019. But the fact that you see different shape dependencies for the matter for the power spectra in the different environments, for instance, if you look at the sigma 8, the reduction of sigma 8 here in voids, which is creating this bump here, is not the same place as in filaments, which is not the same shape as in walls and not the same as in voids. So the idea is that now with the combination of the environments, altering sigma 8 cannot reproduce the effect in all of these environments. And hence, when you combine all of them, you should be able to break some key degeneracies between matter-related parameters like that, and hence improve the constraints that you get over the matter power spectrum only analysis. So to do that, to quantify a bit this ID and see how it performs with respect to the matter power spectrum, we have been using a Fisher forecast, which, as Joseph already presented, is defined under some conditions for the log likelihood that is here assumed to be a Gaussian with a covariance matrix that is independent from cosmological parameters, in which appear the derivatives of your the average of your summary statistics with respect to cosmological parameters and the covariance matrix. So for that purpose, the QOT simulations are really well suited. They have been almost designed for that. And we have been using 500 realizations for the derivatives and 7,000 realization for the fiducial of the fiducial cosmology for the numerical computation of the covariances. So the Fisher information matrix allows you to derive here on the table, in the table, for instance, the 1 sigma marginalized constraints over all cosmological parameters, and here the 1 sigma confidence ellipses for all pairs of cosmological parameters and over the nuisance parameter, for instance. So the first thing we can notice is that the matter power spectrum is creating in the corner plot really elongated ellipses, which are signatures of strong degeneracies between parameters of the model. And for instance, the environmental spectra on the side are showing different information. For instance, here I'm showing a zoom over the mu and omega m plane, and you see that filaments, voids, walls are getting different orientation, which when combined all together is leading to a shrinked ellipse, the blue one in the inside, and a marginalized constraint over these two parameters that are of improvement over the matter power spectrum of 8 for the omega m and 15 for the summed neutrino mass. And this is exactly the same idea, for instance, for mu and sigma 8, where you see that the combination is even leading to an ellipse that has an almost orthogonal orientation than the matter power spectrum, which suggests that if you combine these environments with the matter power spectrum, you can even shrink even more the constraints that you have. So the other thing that is interesting to see in this table is the fact that the best environment that is individually performing the best for the sum neutrino mass is the void environment with the 2.4 factor, while for the others it's much less, which is also something that is advanced and that is shown in other studies. And also you see that nodes environment is the one that is getting the poorest constraint due to some strong correlations in the correlation matrix that I don't really show here, but this is the idea. What about redshift space? Now we know that in redshift space you can break some degeneracies by using the information that is contained in both the monopole and the quadrupole of the matter power spectrum. already using only the monopole, you are getting some tighter constraint on some parameters. For instance, the sum neutrino mass, which is 0.4, while it was 0.9 in real space. But the combination of spectra of the different environment is still getting some improvement. For instance, a 5.5 improvement factor for the sum neutrino mass and 3.8 for the sigma 8. And using the monopole plus quadrupole is shrinking a lot the constraints that you have on these two parameters, for instance, with a 0.08 on the sum neutrino mass, but the combination of spectra is still leading to some interesting improvement, 2.4 improvement factor for the sum neutrino mass and 2.3 for the NS, the initial slope of the initial matter power spectrum. While, for instance, you see that for sigma 8, you are not improving the constraints, and that is already quite shrinked when using both the information. So the question we wanted also to ask is how these constraints are evolving with the maximum values of the spectra that we are using. We have been seeing that I was using the 0.5 H per megaparsec for the previous plots, and we wanted to see if this was true also, that the environments are getting better constraints than the matter power spectrum at all scales considered, which is apparently true for both real and redshift space. Something that you can notice is that the matter power spectrum is getting saturating in both cases. For instance, in real space at 0.2 or 0.25, you are not improving much by going to smaller scales. What it also seemed to happen. Yeah. It also seems to happen at smaller scales, but for the combination of spectra, but at much lower values of the marginalized constraint. And this is also true in redshift space, except for sigma 8, where you have the overall improvement factor of around 1 everywhere. So yeah, I've been showing you that the spectra computed in the different environments as defined by the T-Web algorithm have different shape dependencies that you can use and that show different impact of cosmological parameters that you can use to break some degeneracies and gain considerable improvement factor over the matter power spectrum analysis from 4 to 17 in real space and from up to 2.4 over monopole plus quadrupole analysis of the matter power spectrum in redshift space. And this is also true for all the considered scales from 0.1 to 0.5, and I didn't show it, but it also yields a better SNR than the matter power spectrum in all cases. So the next question for us is, can cross spectra improve even more the constraints that we get, and how can we apply this on matter tracers like halos or galaxies, which will come with a need to integrate bias terms in each environment and all, so with additional difficulties that we need to work out. So yeah, thank you for your attention, and I hope it was not too blurry for you to hear, so I'm sorry for that.
Oh, thank you very much, Tony. At least I could hear you quite well. I hope all the attendees could the same as well.
Sorry.
No problem. No worries at all. So questions for Tony? There is 1 or few minutes for questions in case. Otherwise, if there are no questions, of course, you can ask offline questions through the chat or through directly by email to Tony. So, okay, thank you very much again, Tony. And we switch to the next speaker. So we have now, Irene Arkangelskaya talking about the results. Good morning, good afternoon. The results of analysis.
I'm sorry, I need 1 minute because I have problem with internet connection.
Okay. So if you wish, we can swap.
Okay, we can change.
Yeah. I can. We can give the floor. Yeah, okay. We can give the floor to the next speaker if.
Okay, and I will be your last speaker.
Okay. So okay. Carlos, are you ready?
I'm very sorry, but
no problem. No, don't worry. I hope you managed to fix. So Carlos, are you ready?
Yes, I'm here.
Thank you so much.
Give me a second to
share
the slides.
Take your time. No problem. So actually, your talk was perfect as the closing one, given the title. So closing the cosmological loop with the redshift drift. Okay, so last but one talk. Thank you very much, Carlos.
Thank you. So hello, everyone. So my name is Carlos Martins from the Center for Astrophysics in Porto. And here's my email if you want to contact me with some follow-up questions. Yes, so I want to report on some work that we've been doing in Porto. So this is mainly work of some students of mine. And by way of motivation, we all know that the universe is recently accelerating, and this evidence for acceleration strongly suggests that our canonical theories of cosmology and particle physics are incomplete, and there's new physics out there waiting to be discovered. And one of the tasks of current and future astrophysical facilities is to search for, identify, and ultimately characterize this new physics. So I'll tell you a little bit about the work we've been doing in relation to the redshift drift. So for those of you who don't know what we do, so the Cosmo Espresso team uses precision astrophysical spectroscopy and a bunch of other theoretical, computational, observational tools to try and characterize the acceleration of the universe, try and understand if the laws of physics are universal, and so on. So we're deeply involved also in instrumentation, so things like Espresso or the LT, and we also pay some attention to education and outreach, which is off topic for this afternoon, but which I'm happy to tell you about some other time. Okay, so I want to start by reminding you that basically almost all results that we get in cosmology are model dependent. There's very few examples of astrophysical observations or experiments that are not model dependent. And one of them is the redshift drift. Now, you already heard an introduction to the redshift drift, so I won't spend too much time repeating things. I'll just emphasize that it's a direct, non-geometric, model-independent mapping or measurement of the universe's expansion. It's independent of gravity, it's independent of geometry, it's independent of clustering. So the specific conceptual difference is that we're not mapping the present day past light cone, we're directly comparing different past light cones. And this can be done in a model independent way. Now that said, you can of course use these measurements to constrain specific models or model parameters therein. And here, the redshift drift measurements are not the most tightly constraining in general by comparison to other facilities, but they do break parameter degeneracies because they have sensitivities to cosmological parameters that are typically very different from the ones of standard probes. And here as a simple illustration, here's an example of constraints on a model from the redshift drift in red, Planck in blue, and you see that the contours are pretty much orthogonal, and by combining the two, you can get significantly stronger constraints. So the canonical way of doing the measurement is by using the ELT, so that's the most studied case. But there's other possibilities, including SKAO, intensity mapping experiments that have already been mentioned, and so on. It has also been said already that in practice, what you measure is a spectroscopic velocity, and I want to emphasize that the feasibility of measuring signals at centimeters per second per year has been recently demonstrated in using the HARP spectrograph. There's 2 papers last year that demonstrate that this can be done. We're currently doing tests with the Espresso spectrograph, which will be much closer to what the LT will do. The important point for the next few minutes is that the redshift drift and the spectroscopic velocities are related by factors of 1 plus z. So they have different redshift dependencies. And this is illustrated here. So for a fiducial lambda CDM model, you can see as a function of value of omega matter, the redshift of 0 drift, or when you switch from positive to negative drift, the maximal positive drift and the maximal positive spectroscopic velocity. So all these things are different. And this is important if you want to use these measurements to constrain cosmological parameters. So these sensitivities will be redshift dependent. Correlations between parameters can change sign. And this is something that one has to take into account for optimization. This has been discussed in a paper by Alves et al. And we have some new results that have been submitted. We're waiting for the referee where we discuss this in a little bit more detail. I also want to emphasize that the redshift drift is pretty much unique in that the signal grows linearly with time. So the more you wait, the better is your signal, even if you do nothing else. Okay, so first, let me give you an example of sensitivities to cosmological parameters. So if I take the usual CPL parameterization of dark energy, what you see plotted as a function of redshift is the sensitivity of the redshift drift and the spectroscopic velocity to each of the 4 parameters. So Hubble constant, omega matter, W0, and WA. And you see that for the Hubble constant, the sensitivity changes signal with redshift, what the other parameters it doesn't. You also see that for omega matter, this curve is monotonic. So the deeper you go in redshift, the more sensitive you are to the matter density, which of course makes sense. For W0 and WA, the maximum sensitivity is around redshift 1. Why does this matter? Well, let's take a simpler case of flat lambda CDM, where you just have omega matter and Hubble constant as free parameters. So if I do 2 redshift measurements, 2 redshift drift measurements without any priors, and I use these 2 measurements to measure both parameters, if I make the 2 measurements at low redshifts, the 2 parameters will essentially be fully correlated. If I do them at high redshift, the 2 parameters will be fully anti-correlated. But there is a choice of pairs of redshift where I do the 2 measurements, where the 2 parameters will be uncorrelated. So this is shown by this black line. And you see, so you typically want to do 1 measurement around redshift 1, around redshift 2, another one below redshift 1. You can see the impact of this effect in the plot on the right. So if I do a measurement of the redshift drift or several measurements of redshift drift to the LT, the constraints I get on the omega matter H parameter are this blue ellipse, so strong degeneracy. If I do it with the SKA, I get the green ellipse, again, a strong degeneracy, but the 2 are pretty much orthogonal. So if I combine the 2, I get much, much tighter constraints. Okay, now, as I said, the standard method of measuring the redshift drift, which has been proposed by Linsky et al., uses Lyman alpha and metal absorption features along the line of sight of bright quasars with a baseline experiment time of around 20 years, although some recent developments mean that this number can be lowered, maybe by a factor of 2. You can only measure around about redshifts above 2, because below that Lyman alpha forest falls in the ultraviolet. And the predicted spectroscopic velocity uncertainty has this shape. There's a prefactor here, which I'm going to keep in what follows as a free parameter. Last year, in the context of the Astro 2020 decadal survey, there's a white paper proposing what's called the cosmic accelerometer. The idea is that you use essentially commercial off-the-shelf equipment, so smaller telescopes, smaller detectors, to do a much cheaper experiment, and possibly also with a smaller experiment time of about 6 years. This was just a white paper. There was no detailed study, but we're going to take their prediction of the sensitivity at face value, again, in what follows. Ryan Cook has also proposed what's called a differential redshift drift. So the idea is that instead of comparing some high redshift source with the reference at redshift 0, you measure the differential drift between 2 non-zero redshifts. The idea here is that given the shape or the predicted shape of the velocity, of the spectroscopic velocity as a function of redshift, there would be pairs of redshift for which the spectroscopic velocity signal will be larger than if you compare to redshift 0. So you're just giving yourself a better chance to detect the signal. And this is, of course, legitimate in principle. But the point is, the fact that you can detect the drift more easily does not necessarily give you better constraints on cosmological parameters. So it depends on what your goal is. So in this case, the quantity that you measure, or the relation between the spectroscopic velocity and the cosmological parameters will be like this. So the idea is that we have some high redshift source, but you typically have many absorption clouds along the line of sight, so you can get information about intervening redshifts. Okay, so what we did recently is a sort of a comparative study of these different methods for the purpose of constraining cosmological parameters. So here's a slightly complicated slide. So what I'm assuming is I have a single measurement of the redshift drift. I have lambda CDM as fiducial model, and I have some external priors. I'm going to vary the normalization in my spectroscopic velocity uncertainty. I'm going to vary the redshift at which I do the measurement, and I'm going to vary the experiment time. And my comparison diagnostic will be the constraint I get on omega matter marginalizing H0. So there's three parameters that I vary. So you can plot these in various 2D parameter spaces. So the contours here show you equal constraints on omega matter. Black is the usual redshift drift. Red is the cosmic accelerometer, and these plots might be a little bit difficult to interpret, but essentially the bottom line is summarized here. If I compare an ELT experiment with 20 years and a cosmic accelerometer experiment with 6 years as proposed, for the purpose of constraining omega matter, the ELT does significantly better, up to 62% better. So what is plotted in the color map is the ratio of uncertainties on omega matter between the accelerometer and the LT. So a value larger than 1 tells you the accelerometer gets worse constraints than the LT. And the reason for this is quite clear. Even though you might have slightly smaller absolute uncertainties in the spectroscopic velocity in the case of the accelerometer, your relative uncertainties will be larger because your experiment time is smaller. And remember that the signal grows linearly with time. So waiting some time actually helps you. So this also tells you that, so even though you might detect the redshift drift signal more easily with one experiment, it doesn't mean, as I said earlier already, that you get better constraints from that experiment on cosmological parameters, either from the redshift drift alone or when you combine with other probes and want the redshift drift to bring some degeneracy. Okay, so now let's move to the differential redshift drift. So here, to be consistent with the analysis that we have done in Alves et al., we're going to assume we have 5 measurements of redshift drift at these 5 redshifts. So this is the background redshift, so to speak. And I'm going to choose the intervening redshifts at which I do the measurement in 2 different ways. So one is I'm going to fix them at a redshift of 0.67, which is the redshift for which I have the maximal spectroscopic velocity, or maximum positive spectroscopic velocity, for the fiducial lambda CDM model that I'm considering. So I'm maximizing clearly the velocity drift signal. The alternative analysis is we're going to numerically optimize the choices of redshift so that I get the best possible figure of merit in the W0, WA parameter space. So I'm optimizing these constraint W0 and WA. Obviously, in doing this, I'm assuming that I can do the measurements at any redshift that I choose. This is, of course, simplistic. We can do the measurements where we have quasars and absorption clouds and so on. But this is useful to understand how important this optimization is. And the result is, again, what I said earlier, amplifying the drift signal does not guarantee better constraints on cosmological parameters. So this is summarized here. So again, what is plotted is the ratios of uncertainties in the various parameters. So uncertainty from the differential redshift drift divided by the standard ELT1. So a ratio larger than 1 tells you that differential redshift drift does worse. So the first case in these 2 columns, without and with priors, is the case where I'm optimized, so I maximize the spectroscopic velocity uncertainty, and clearly the differential redshift drift does worse. If I had priors, then the priors dominate the constraints on W0 and WA, so essentially I don't gain a lot from redshift drift. But if I optimize for W0 WA, then I can actually gain a lot. So a factor of 20 or 50 or something like that. So again, the message is you should optimize the experiment for the scientific goals that you want. Here is the sensitivity to cosmological parameters, again, in the case of the CPL fiducial model, of the differential redshift drift. And now I have an additional parameter. So on the horizontal axis, I still have the background redshift. In the vertical axis, I have the ratio of the intervening redshift to the background redshift. So this ratio always goes between 0 and 1. And the sensitivity can be positive or negative. And there will be some pair of redshifts for which the sensitivity is 0. So that's why you see this black line. Now, interestingly, there's no black line for omega matter because the sensitivity is always monotonic. And what this means is that if you want to optimize your constraints for omega matter, then the canonical redshift drift is always the best choice. You're always better off comparing to redshift 0, precisely because the sensitivity is always monotonic. So the differential redshift drift here is always worse if you want to constrain omega matter alone. For double constant, a large redshift lever arm is important. So we want to go, we want to have the background redshift at high redshift, but the intervening one at some fraction of it. For the arc energy, so for W0, WA, you want to be sort of at redshift 1 or something like that for the background redshift, a little bit more if you want to constrain WA. So essentially the message here is that in the next decade, these measurements will start appearing, people will start doing them. And it's very important as DLT is being built and high resolution spectrograph of DLT is being built. So its phase V is just about to start. It's very important to optimize the experiment in the right way. So one should decide how best redshift drift can complement other cosmological probes. Of course, we want to detect the signal in the first place. So some trade-offs will need to be made, but the trade-offs are non-trivial and should be understood. So as I said, tests are being done with espresso. The espresso spectrograph will not detect redshift drift, but will certainly have the strongest upper limit by a significant margin. And for the phase B of construction of ELT arrays, we're doing full feasibility studies with simulated spectra, so detailed end-to-end simulations that will allow us to understand a little bit more what the ELT can do and how best to optimize the experiment. So stay tuned. I think the future is bright for these measurements. And with that, I'll stop, and I'm happy to take questions or clarify anything that wasn't clear.
Thank you very much, Carlos, for this nice review and very interesting, intriguing perspectives on this side. So, questions for Carlos? So please feel free to ask any question, of course. Otherwise, you can use the chat channel or contact directly Carlos, of course. Okay, so is there no other questions? No questions? I thank Carlos again. Thank you very much, Carlos. Very nice talk again. And I ask Irene if she's now...
Okay, I'm ready now.
Very good, excellent. And Irene will talk about the supernova redshift distribution based on the Asiago and Open Supernova catalogs.
Do you see my screen?
Yes, yes.
Okay. Just a moment, I try to list it. Op. Sorry, it is not listed. I will show PowerPoint without demonstration. Just a moment. So, do you see my screen?
Yes, yes.
Okay. I would like to discuss the results of analysis of 1A supernovae redshift distribution on data of the Asiago supernovae and open supernovae catalogs.
Irene, sorry, this is a bit small. Can you, if you could, you kindly go into the presentation mode, because now we see it a bit small.
Unfortunately,
It doesn't work.
impossible to list slides in presentation mode. So
Okay.
I can try to use PDF file.
No, go on like this.
Just a
Don't
moment.
talk.
I can open PDF and we try to see it. Just a moment. So, is this situation better than previous one?
Yes, that is slightly better, but still not in full screen. But okay.
Unfortunately,
don't get credit. It's fine.
Occur.
We can read it. We can read it, Irene. Thank you.
So, okay. So, just a moment. The interest of the scientific community of supernovae has increased in the recent years because of several reasons. For example, the intensive study first of supernovae 1987A, which have raised new more fundamental questions with regard to progenitor evolution, explosion mechanism, and nucleosynthesis. Then, in addition, it was make calibration of the absolute magnitudes of few supernovae obtained using the Cepheid variables found in these parent galaxies. And in this case, it was discovery of empirical relation between the absolute magnitudes and maximum and redshift. And then the shape of light course of supernovae have renewed the interest for using such objects as distance indicators because of there is ratio between redshift of this object and brightness. So, also, the homogeneous subsample characteristic understanding is very necessary for investigation of any astrophysical objects, for example, GRB and so on. Usually, the type of 1A supernovae considered as a homogeneous subsample because of suggestion that these luminosity events could be used as standard candles. So, and such wide interest has triggered new, very deep search of supernovae in a few last years. So, the shape of redshift distribution for data of supernova cosmology project is shown of this picture. This data were used for definition of omega and lambda of our meta-galaxy in 1998. And we can see that all this data mostly fitted by power law. Do you see my mouse? Do you see my mouse?
Yes, Irene, we see it. Yes.
Okay.
Thank you. Yes.
I marked the green, but it will be present on several following slides. So now there are 4 big data sets contain data of supernovae of 1A type. ICRANet Supernova Catalog, Open Supernova Catalog, Dark Energy Survey Supernova Program, and the combined Pension sample. So now the Open Supernova Catalog contains data of such different catalogs. Totally, it will be approximately 14,000 of supernovae. So, and then we try to analyze its redshift distribution. So, this plot shows data from ICRANet Supernova Catalog. Part of ICRANet was HZSST experiment data. This data show by white curves. Green circles present permuter data, and magenta Galan-Tolona data which used in this sample. So it's different part of ICRANet Supernova Catalog. You see several different, but totally shape, totally shape comparable. So this is magnitude dependence on redshift for total ICRANet supernova subset. So this green line corresponds to power law fit of permuted data. But if we consider big data from open supernovae catalog subset, we can see that there are several peculiarities in this catalog. So then try to understand what it was. Oh, sorry, what is this? So I'm sorry, I switch screen because of it is seen the graph on this screen, and there are very problem in PDF. So this is plot of magnitude dependence on redshift. Open black circles correspond to open supernova catalog, blue ICRANet supernova catalog, green permuter data, and magenta Galan-Tolona data. And you can see that this peculiarity and data on total open supernova catalog, some different. It's more white in each position. So then we try to plot absolute magnitude dependence on redshift and red is SNLS catalog, and here green is permuter data and magenta Galan-Tolona data. So, and we can see several peculiarities in big sample of supernovae data. So this sample is more than 10 times bigger than ICRANet supernova catalog. And so conclusions. Preliminary results of data analysis show that several peculiarities are presented in 1A supernova redshift distribution at zeta bigger than 0.4, and it could be caused by several reasons. Firstly, some time ago, it was found that there are different scenarios of type 1a supernova explosions, single degenerate and double degenerate scenario. So maybe it caused by absorption in the galaxy, in host galaxies. Maybe it appearance of Ashnull tension, which was discussed on this conference. And maybe this deviation occurs of real changing of parameters of our metagalaxy. A next step will be dark energy survey supernova program and combined Pantheon sample data analysis. And maybe it make clear such situation. So that's all. Thank you for attention.
Thank you very much, Irene. Very interesting. So we got your very important
and question
message.
About standard candles occur.
Yeah, you're right. Actually, when I talk about cosmology with gamma ray burst, I start with the motivations and possible systematics affecting type 1a supernovae. I always mention as an example on why we need to combine together or to have independent measurements from different probes. So you are going deeper into this direction. So thank you very much to you. First of all, are there questions for Irene? Before I leave the floor to Massimo for some remarks, and then Michele, and then to all of you for discussion. If not, I would leave the floor. I thank, first of all, very much all the speakers, Irene, and all the previous speakers of today and also of yesterday. It was a very interesting and nice overview of the status and perspective and the high potentialities of all these probes. For one side, complementing the most popular, or let's say so-called standard probes, and to get clues, hopefully, to the main question marks that are still affecting modern cosmology. So I leave the floor to Massimo for his considerations. Thank you, Massimo.
Hello.
Hi, Massimo.
Yes, I'm talking from the dark.
Yeah.
I will be very short because we are really close to I think, to the physical ending of this session.
Yeah, we have 10 minutes.
Or the Zoom session, I mean. So I was considering, I was asking myself about the importance of these 2 days discussion, and to give you the taste of what I think is just imagine for a while that we can measure H0 only through the cosmic microwave background. At this point, we conclude that H0 is about 67 kilometers per second per megaparsec. Everyone is happy, and that's it. No, in fact, the situation is much different. Thanks to the possibility to measure H0 and the other cosmological parameters in a completely independent way. And this is one of the basic principles of physics, to measure the same physical quantities through independent experimental methodologies to keep under control the systematics. Well, this give this possibility has produced 2 results. First of all, the expansion rate of the universe can be different from 67 kilometers per second per megaparsec as measured in, let's say, in the early from the observation of the early universe. And secondly, we have these 2 scenarios. One is very, let's say, sexy, charming, the possibility of go through a new physics. And the other way to explain this discrepancy between early universe measurement of H0 and let's say H0 measurement obtained with local indicators is that this is due to, let's call them, trivial systematic errors. And now, the idea that I made in these 2 days of discussion is that probably the H0 dichotomy will be not solved through keep going to use standard local indicators and comparing the result on them with the CMB. I think that what we have just listened by Carlos a few minutes ago, the cosmological drift, or what we listened at the beginning of this session by Daniel, through the possibility to use the gravitational wave as methods to measure H0, these to me appear the most promising possibility to solve the apparent dichotomy between Planck and local distance indicator measurements of H0. Then there is another aspect that that was emerging, and this will really on gamma ray burst, quasar, voids that personally I didn't know before listening the talk of Pisani. And I think that we can help a lot in studying the evolution of dark energy with redshift. So in other words, how as a small w will vary with redshift, with Z. Oh, I mean, I don't have nothing else to add, and I think maybe we still have 5 minutes to discuss.
Yeah, thank you, Massimo, for your considerations, of course, and maybe Michele would like to get his general comments. Thank you, Michele.
Yeah, my general comment is that I was really happy of this parallel session because I think it complements really well what was discussed yesterday in the plenary session, where basically there was a very interesting and full description of the tension from the perspective of the main probes. And as Massimo was saying, I think that having the possibility of adding to the pot additional alternative method.
Michele, sorry to break you for a while, but I was focusing on the aspect that we have discussed today in my short speech. I didn't mention the chronometry, the cosmic chronometers, because we have discussed yesterday, just to be clear.
No, yeah, I knew it. And I think it is extremely promising for the future because from my point of view, we saw that we have many alternatives that we can explore and on which we can build for future development. Basically, this I don't want to add more with respect to what Massimo already well wrap up. So I would say that if there are some questions from the audience, that some more topic that the audience wants to ask to the speaker, if not, I think we can also close. So if you have any question, please, you can go.
Yes, I would just remind all of you that all the sessions are recorded, so you should receive by the organizers an address pointing to YouTube, where you can find the recording of both the plenary and the parallel session, isn't it, Michele?
I think so, yes.
Yeah. Of course, if you wish, you can contact the speakers to get the PDF or the presentation of the slides. I think, or it may also be a good idea to collect them. No, Michele, it's very interesting.
Yes, I think there is also the possibility to post them directly in the timetable
on the Indico. Yeah.
On the Indico, yes. I saw other session that done it. So maybe we can ask the speaker if they can post it there so that everybody can have access to the presentations.
Yeah. So yes, and of course we remind that Michele is coordinating this great effort of a living review of non-standard cosmological probes, which is really a very important effort, as we have seen during these 2 days. And many or most of all of you are actually involved. I think that those of you who are not involved could contact Michele in case they wish to provide suggestions. This, I think, will be ready hopefully by September, October, no, Michele? Something like that.
Hopefully, yes.
It is aiming, yeah. So it is aiming at being a reference for this kind of probes. So, if there are no further comments or discussion, also from my side, I thank again all of you. I thank, of course, Michele and Massimo, the co-organizers of this sessions, of course, and Michele for his great efforts specifically. So thank you very much to everybody. And I leave, of course, the floor to Michele and Massimo for the last goodbye. Yeah.
I'm just saying goodbye also from my side. Thank you very much to all the speakers and attendees.
Massimo, you're muted, by the way.
Oh, ok, va bene. Buona serata a tutti.
Grazie.
Thank you
so much, everybody. Ciao.
Thank you. Bye bye.
Buona serata. Thank you. Bye.
Thank you. Bye bye.
Grazie.
Ciao.
Ciao, good you. Bye.
Bye.
Bye bye.
Ciao ragazzi, grazie Gregory dell'assistenza.
Siamo rimasti solo noi?
Adesso possiamo cominciare la discussione vera. Allora, ma quel rigore c'era o non c'era?
Recording.
Cioè, ragazzi, alla fine con la ragazza russa roba.
Aspetta che, scusa, ecco, un attimo.